A very warm welcome and a very good afternoon to all the participants for the final day of our faculty development program. It has been a wonderful journey of learning, interaction, and knowledge sharing over the past days. Your enthusiasm and active participation have been the driving force behind the success of this FDP. As we step into the conclusion session today, we look forward to another enriching and memorable experience together. So we are going to start the first session for the day. And yeah, it's my great pleasure to introduce the esteemed speaker for the day, Dr. Ujjwala Barambe, who's working as an associate professor, an academician, and researcher with 23 plus years of experience at the intersection of artificial intelligence, machine learning, data warehousing, and mining, natural language processing, semantic technologies, geospatial analytics, and education. She obtained a PhD from IIT Bombay in semantic geo-ontology matching, multiple publications in IEEE, Elsevier, CRC Press, passionate about AI for social good, NLP, and federated learning in healthcare, education, and environmental domains. She has mentored 100 plus UG PG projects in ethical AI, NLP, and predictive analytics. She is a panelist at IIT Bombay, editorial board member for CRC Press, reviewer for ICACC NCATM, co-organizer of national FDPs on AI and geospatial computing. Our core focus areas are NLP and multimodal deep learning, semantic web and ontologies, curriculum innovation, Smart India Hackathon mentor, emotional intelligence and counseling in academia, AI driven educational system. It is my pleasure to warmly welcome our distinguished speaker, Dr. Ujjwala Barambe, who will be delivering today's session on the highly advanced and impactful topic on scalable deep learning architecture for real-time geospatial data processing. Ma'am, we are delighted to have you here, and actually we enjoyed your first session where you took us into the different ML techniques and algorithms with the geospatial data. So even today we are so excited and looking forward to gain valuable knowledge from your experience and research. Thank you so much, ma'am. Over to you.
Uh, Thank you, ma'am. It's really wonderful that you introduced so well. Uh,
Thank you.
so let me start. So is my screen visible?
Yes, yes, ma'am.
Yes. Okay. So guys, it's a last day, so I can understand. And my topic is also a little different, but I discussed with Anagha and I have little changed the course of my topic today. Um, so what I decided, rather than focusing more on a deep learning architecture, I will again start or continue the journey which I have started from ML, and I will go towards a DL, that is deep learning. Then I will go towards generative AI. I will go towards little bit of agentic AI. I also wanted to go towards little bit of a symbolic AI, and a little bit of fundamental and mathematical concept, and more focus on the case studies. Some of the case studies, one case use case I will take, and I will tell you that how all these technologies can be applied. And I'm also going to showcase some of my student project. Those are obviously undergraduate student project. So just to get an idea that how we have implemented. So that is what my today's agenda is. So I'm not focusing more on the deep learning architecture, but yes, I'm going to focus.
हमको तो आना पड़ता है अभी मुझे रात को 8 बजे तक बैठना है
Uh, can you mute, sir? Yeah. So I'm going to more focus on two major architecture. One is a CNN based architecture, because that CNN architecture is important from the perspective of deep learning. And then I'm going to focus more on a little bit of a GAN architectures, which is basically more towards related to generative AI. So let us start. Uh, So guys, before starting, I was just thinking that, how to open the topic and how to look at from the perspective that how this evolution has been occurred. So then I do remember something called as Rubik's Cube, because it is a kind of a cube which considered to be one of the problem solving kind of a problem. And specifically from the childhood, when we appeared for scholarship exams, or when we train the children for the problem solving, we generally take this particular as example. So this is a Rubik's Cube. And if we want to solve this particular problem, what do we have is that we have different colors on the each this face, and we just want to match these color. Like for example, maybe at a one end a red color, maybe at a one end at a green color, so on and so forth. Now, given this particular problem to any, say, 5-year-old or 6-year-old, because we are, as a human, we are always a color sensitive. So maybe in the first stage, what he will try to understand is, how can I actually move? So I can move this in one particular way, and I can move this in a 3-way. So maybe in the first way, when he will try to solve this particular problem, he will try to see, okay, so these are my 2 colors. So maybe I want to make this as a third color. So maybe what I will do is that I will move in this manner, and I will make this as a 3. Then I will try to make this as a blue. Then I will try to make this as a orange. So what we are trying to do inherently at the first phase, when we take any problem to solve, is that we take something called as a feature. So that feature, we will use it for certain kind of a prediction, or kind of a, learning, or giving some kind of output. But what happened is that for every problem, we do have something called as a layered approach. Like for example, if I'm going to move in this particular first step, then I can move this is in a different stage where I can make it in a red. So what exactly happened is that rather than thinking one problem in a very simplistic manner, what we can do that we can add a certain kind of a layers. Now our human brain is already capable of doing this thing using neurons and lot of things. So we have come up with certain mathematical structure of the human brain, which we called as a pattern. Which we called as a deep learning. And that deep learning models are quite capable of learning the pattern. So obviously they try to learn the pattern based upon certain features only, but those patterns are specifically a layered pattern. Okay, so you may have a different layered, and from those different layered, we will try to solve this Rubik's Cube. But then what we need to do is that if I'm going to move this into a one particular manner, then next move will be this. The third move will be like this. So what do we have is that we have certain instance or a history as a background in our mind. And if we want to, based upon that, if we want to, rather than creating only a next step or a next pattern, what I can do is that can I create the new states, or can I create the new move, so that ki baba, it will be from 1 2 3, it will get match and you will get the solution. So then we will move towards something called as in our term called as a generative AI, where there will be some instance as an input, and I'm going to create instance as an output. Okay, so in this particular case, if I'm going to use generative AI, if I have a certain images as an input, I can directly create image as an output. Okay, rather in a deep learning, it will be some kind of a supervised or unsupervised kind of output which we will take. Okay, so next is we have something called as a LLM, which we called as a large language model. Initially, LLM used to take only specific type of a data, but nowadays it may take different types of a data. Specifically in context of geospatial AI, we will talk it later that what LLM can do now or what it cannot do. But what exactly they are good at is that they are kind of little smarter than the other. Obviously, LLM is also part of a generative AI, where for the each cube, it will try to reason each and every whatever steps which we are performing, and it will try to generate the next smartest move based upon that particular trajectory. So that is what exactly mean by LLM, and that's the capacity of LLM. Now we wanted to move towards something called as a one again level of agentic AI. So suppose child who is going for a class of a Rubik's cube solving, he may have a 10 session, and then in course of a time, okay, he will try to learn something. Like for example, it may not be a right example, but like for a final year students, if you compare first year engineering student and if you compare final year engineering student, they become more smarter. We cannot express the way they become smarter, but they always smart. Why? Because those 3 year ka automatic learning they have done. So they already know how to study. They already know how to do submission. They already know how to manage the teacher. Okay. So the thing is that when we have something as a memory and a strong memory, and based upon that we have certain knowledge. Now, based upon that, if you have a AI who can understand the current state, based upon that it can perform some kind, can give you some kind of a plan, or if it can execute certain kind of a action. Okay, it can also check your mistake and it can also improve those mistakes. Then we call it as a agentic AI. So in agentic AI we have a kind of a parallel programs or a parallel agent which are running, which are coming together to solve a particular task. So I can have multiple agent, okay, only for solving the red part or only solving for the green part, and then I can solve this particular Rubik's rules, actually performing the move by using agentic AI. Okay, we also have one of the I'm really sorry, one of the other type of AI which we called as a symbolic AI, which is also a little bit of a it is not a new kind of a AI, but it is something called as, which is based upon a basic AI principle of reasoning, okay, or a logic. So I don't know how many of you know, but we all have learned something called as a proposition logic, predicate logic, and there are different order of logics which are there, which is also one of the significant part of AI. So if you use these kind of a memory mechanism for the purpose of reasoning or inference, then we call that AI as a symbolic AI. Okay, so these are the different. Obviously, in these AI, there are other different types of AI. We talk about a conversational AI or other different types of AI, but these are the major categories of AI in which in today's session I am going to talk about how to correlate and what are the different use cases are there in the geospatial domain. So how geospatial domain is intersecting with these different kind of AI, and from that we what kind of a problem which we are trying to solve it for societal contribution or for a societal good using a geospatial AI. Okay, so what exactly we want to remember here is that ML is specifically, it's a kind of a learning mechanism to learn a certain kind of a clues. DL is specifically used for pattern recognition and pattern understanding in any problem state or in any domain. Generative AI is specifically used for pattern creation, okay, because it generates a pattern. LLM is specifically used for pattern prediction. So it will generate the next instance of certain prediction. Agentic AI, our goal is to create a pattern action. And symbolic AI is specifically for understanding the pattern logic. Okay, so this is a very generalized, a broad idea, analogical idea for ML, DL, generative AI, agentic AI, and symbolic AI. Now, let us little bit go ahead and understand that what exactly, how we can match these different types of AI into the geospatial domain. So guys, just give my screen is
Yes, ma'am, it is visible.
uh, okay. Okay. Uh, So what we are trying to do, so we last lecture we have seen a lot of different types of machine learning, and now though I think at the last day you must have heard lot of machine learning problems and how it can be applied to different types of data which are available in geospatial domain. Like we have as I told you last time also, it's a kind of a big elephant where there are different people think from the different perspective, because there are different types of people who get involved, there are different types of data which come together, for any geospatial application. So we do have a SAR data, we have a hyperspectral data, we have a IoT data, we have a different types of data, and on which we are performing a kind of a processing, and these processing mechanism or methods we are discussing. In these methods, we are now discussing a broader domain of machine learning. So we have a one big domain, which is AI now. In AI, we have a machine learning. In machine learning, we have a deep learning. In deep learning, we have a generative AI. In generative AI, we have one intersection of LLM. And again, we have one intersection is called agentic AI. And we have again one intersection of symbolic AI. Okay, so this whole bigger landscape in which I am little bit discussing in a very smaller way today. Okay, so in machine learning, what we generally do, we actually have something called as a raw data. Then we perform something called as a feature engineering. Then we perform something called as a machine learning algorithm, and then we get an output. Like for example, I have some raw data about the crop risk prediction, that what is the risk to to have a sugarcane crop or something like that. Then what I will do is that I can have a raw data which may be a weather data, which may be a crop type data, which may be current crop conditions, and then I'm going to perform some kind of a feature engineering, and that I will go give it to a standard machine learning algorithm like SVM, XGBoost, and based upon that, I'm going to create a score. So this will be, because I'm creating a numeric value, this will be my, kind of a regression kind of a problem. So in this, there are different types of feature we extract. We specifically with respect to geospatial domain, we extract something called different types of indices, or we can take a directly image, and from that image we can extract the features like the object detection or segmentation or texture or shape, or some kind of a distance to river, which we have seen in last lecture. We were doing something called as a beehive placement. So in that, the distance to river was a very significant kind of a parameter. So we are going to extract certain kind of features, and then based upon those features, we are going to give some kind of output. Okay, so many times, as we have seen last year, there are various classification of ML algorithm, but generally we have a supervised algorithm and unsupervised algorithm, where supervised algorithm is very popular in the ML domain, okay, which we called as a classification algorithm or a prediction algorithm. So there are different kinds of example like landslide prediction, or there are different types of example for machine learning. Now, next type of problem. So next type of the intersection from deep machine learning is deep learning. Now, one of the major difference between machine learning and deep learning is that the feature engineering step is been removed. Okay, because what exactly we are doing here is that for a different types of a data, we have a different types of model. Okay, we have a specific kind of a mathematical operations which we can perform on the data, so that we don't need to rely on the manual feature extraction. Because what happened with the machine learning domain is we call it something called as a curse of dimensionality. That means that how exactly you are going to extract the features, how many are they, and how they are interdependent on each other. It may possible that it may create a very high dimensional space, or it may create on a low dimensional space. So what I mean by that? High dimension space matlab there are many features. Okay, some of the features are significant, some of the features are not significant, but still there are many features. Rather than that, a low dimensionally problem. Many generally the the textual problems are a low dimensional problem, because initially if you have a text, how are you going to represent the text in terms of a numbers? Because what exactly the purpose of feature engineering is to specific in geospatial domain, we have some natural phenomena. From that natural phenomena, we are going to have some devices from which we are capturing that instances. Those instances in a different format, and those format we are going to convert in terms of a machine processable unit. So machine processable units are basically a numeric unit. So generally we convert it in terms of a vectors or in terms of a matrices. So in this particular gap, it is, if we are using machine learning, then machine learning uh, uh, will be hand curated feature, which we say. And so it will be your model will be very much depending upon the features which we are trying to use for your solving the problem, rather than the actual phenomena. Okay, rather than the actual phenomena. So that was one of the biggest problem with the machine learning algorithm, and that is why we have a deep learning algorithm, where your deep learning algorithm itself is going to perform some kind of a processing mechanism, so that it will convert those feature into a machine processable unit. Generally, as I told you, it will be vector or it will be matrices. तो सबसे ज्यादा फेमस आर्किटेक्चर जो है in the deep learning network is a CNN. CNN इसलिए है geospatial domain में क्योंकि there was I mean it was an era where images used to dominate a lot a geospatial domain. Nowadays, last year I have given one lecture on text processing in geospatial domain, and at that time there was not much of the LLM or LVM was there into the for geospatial reasoning or analyzing. But today I was looking at it, there are so many now LLMs are available. So textual processing is a possibility in 2025, which was not earlier. तो बहुत ज्यादा डोमिनेशन था इमेज प्रोसेसिंग का, एंड दैट इज वे CNN का बहुत ज्यादा डोमिनेशन था, बिकॉज डीप लर्निंग base image analysis we can perform only on images. I mean, you can use CNN for tabular data as well. People have used it, but the thing is that mostly it has been used for images, jahan pe we take images as an input, we perform some kind of a convolution mechanism to extract the feature. It itself extract the feature which we called as a feature map, and there is a then whole CNN architecture where we have a input layer, output layer, hidden layer. We have certain activation function. We are going to see in few minutes in detail. We perform some kind of a pooling operation, and then we give some kind of output. Okay, तो classification के लिए जो बहुत popular है in the geospatial domain is a CNN. Segmentation के लिए, because object segmentation is a very significant problem in geospatial domain, तो उसके लिए जो generally use होता है वो होता है encoder decoder architecture style, which is many are there, but UNet is again very commonly used kind of architecture. जहाँ पे you take images as an input, it will go to something called as an encoder. Encoder is also a one deep network kind of architecture, but it will actually kind of represent your image in a very compact form. Okay, and then it will go to the decoder image, where based upon that compact form, it will generate the based upon task some kind of a output which is called as a decoder, and then the output will be given. Okay, so basically CNN objective, when it will perform the feature map, it will basically try to learn the edges or the texture or the objects, so on and so forth. Rather, UNet give a kind of UNet process each and every pixel, okay, with certain kind of a mask, and it will try to identify the pixel base, kind of a object segmentation or something like that. So there are many examples in geospatial domain. So we use, I'm also going to present classification, image-based classification is a very popular problem. Okay. So next kind of AI, which is also important, is a generative AI. So generative AI is also very broader area. There are many models which are there in generative AI. But I'm going to now focus only on the two models for this presentation. One is the generative adversarial network, and another one is a diffusion model. Okay, so what is I don't know how to tell you this, but in 2014 and 15, I have attended a Professor Goodfellow lecture in IIT Bombay, and you can't imagine how difficult it was, for us to generate the multiple instances. You can't understand how difficult it was, and generative AI or a transformer architecture which is there, and the way the Vaswani's paper came, attention all you need has completely transformed the whole AI field. And I do still remember in that lecture when he was explaining everything. What happened here is that because earlier what we were doing, I have a multiple object, like I have a certain data which is from with the 100 instances, but I'm just able to classify those instances based upon some classes. जैसे for we can say कि अगर I have a 100 images of a flood, so I can have an output as whether this particular part is damaged, not damaged. Okay, like we have also worked on certain area where I will take some historical data and I'm going to classify whether that area is slum or not slum. But what GAN has done, or what generative AI has done, I can take the 100 images and I can create 5 images based upon those 100 images. This is the most the evolution which has happened. You have to understand it, that how difficult it is, that like for example, if I'm going from, like I generally travel from Bandra to Bhandup, but then I have a multiple hops. So when I'm starting from Bandra, if I can predict my whole path based upon all parameters which are present, will be my generative AI, because I can generate multiple instances at a time. So there is one, I mean, you can understand the significance of it. The one thing which I remember, which is not there, but just now I remember in 2023, when I was in US for IGRAS 23, I still remember there was one whole session on something called as a synthetic data generation. Okay, which is basically the job of GAN. So what he was telling me, that there is a group of people who are studying the Antarctica ice melting. And you know that in Antarctica, the 6 month, there is no absolutely sun. It is not habitable. Even in when summer will start, there are few months when ice start melting. It is very risky to go there and to get the temperature. Now, because of the climate change, there is a huge amount of attention has got for Antarctica ice melting. So what he was telling me, what he was presenting a paper on GAN-based synthetic data generation. So what he was telling me, that if I want to get a temperature, or if I want to get a data from the ice, I need to actually go and put the device, and then go to the ice, and then from the ice depth with the radar, I need to get this, the depth of the ice, and the temperature of the ice and everything. But as we already have 20 years ka data, I can at least take only few actual sample, and I can interpolate other sample using GAN. So this is the way generative AI actually socially can contribute. That means that it will, because there are few parts which are very difficult. So using synthetic data, okay, it will be very easy for us, to study or to model. Okay, like for example, we wanted to work on certain one project which we haven't actually got the data and we couldn't complete it. But for few part which we have started is that in India, specifically with respect to the soil analysis or a water analysis, because it is very significant resources, but getting the data from the various at the equal distribution, because we require a representative data, many times we don't get that equal data in a particular zone. Okay, because the terrain of some zones are good, some zones are like if you go to Jalgaon region, those region are considered to be soil good region. Why? Because they have a crop like banana. Banana is a phosphorus rich crop, so obviously their soil will not degrade as the sugarcane crop or Kolhapur region or some Pune region crops, because the most of the time sugarcane generally absorb so much nutrition that it doesn't have or keep some nutrition in the soil. Okay, so these where we already know these characteristics, I can use the generative AI model to generate or to generate or to support my data so that I can perform some kind of experimentation. So one of the very common thing is to remove the cloud cover from the satellite image. So I have a satellite image and it's a cloudy image. And from this cloudy image, I'm going to give it to the first to the a GAN network where it will perform two model architecture, generator and discriminator. So generator will clean the output, discriminator will evaluate the output whether it is according to the requirement, so it is a real or a fake. It will manage the loss accordingly. It will give loop to the generator. Generator will again generate and evaluate. Okay, till certain iteration, it will perform that so that you will get a cleared image, which will not be a cloudy image. Okay, so this is one of the GAN architecture. Another architecture is a basically diffusion architecture, where rather than having two architecture like GAN, we do have a noise based kind of architecture where I can have we use impute the noise in the images and then we start denoising it. So based upon noise, inputting the noise and removing the noise, we will perform some kind of a mathematical operation, which we are calling as a diffusion model. So the generative AI model, which I talked about, are specifically used for generation. Okay, so pattern generation. One of the examples are cloud removal or synthetic flood scene generation, something like that. The next is a kind of a large language model. Now, large language model are specifically one of the part of something called as a natural language processing. So what is natural language processing? Essentially, when your input data is a textual data, okay, or it's a language data, then we are performing or we are trying to give the understanding of that language to the computer. That process we called it as a natural language processing. Okay, but the thing is that before 2021 or 22, because the languages are geographically and temporarily very dynamic phenomena, I can use the word. What I mean by that, the way we are speaking now, maybe we were not speaking 10 years back, even in Mumbai, or the way I'm speaking, the Marathi in Bombay may not be similar to the Marathi in Pune. But do they differ a lot? The answer is no. Do they change? Yes, they change. But how much they change? Maybe very gradually. So the thing is that language has its own different spatio-temporal phenomena. And that is why specifically for machine learning model, it was very difficult to process the natural languages. Why? Because machine learning models are specifically you need to capture the features, and based upon that features, we are going to perform some kind of a classification or clustering algorithm. So, many years till now, the students are doing whether the data is a fake or not fake. I mean, the news are fake or not fake. So these are kind of a text classification algorithms or text classification problem. But the problem with the language processing with respect to textual processing is that the features which we take from the language, because we convert that text into the numeric form, that's what exactly the feature engineering does. Many times we lose the meaning. Okay, like for example, if I say I am happy today, okay, I am not unhappy today. So actually both sentences are same, but how does computer understand the not and an is actually happy? Okay, so these were the problem with the traditional machine learning in NLP. So what happened is that as the data driven architectures has increasing, I think the Google was the first who has a lot of data, and they, because their Google search engine, they are very good player in NLP. But the thing is that data get accumulated with respect to languages a lot, and later on, because of the evolution of deep learning, generative AI, explicitly with respect to encoder decoder architecture style, where encoder is going to understand the pattern and compact the create a compact representation, and decoder will take that compact representation and can generate based upon the task. Okay, that get simulated. And then there was one big revolutionary paper has come called as attention all you need. Okay, in which attention based, because in languages we don't need to remember, or we don't need to consider a lot of features or a lot of all the words which are there in the sentences. Like for example, if I'm speaking for an hour, I don't think so ki after 1 hour, if somebody who is listening really very patiently or very sincerely, he will able to generate more than a 15 word or a 20 word, or maybe 2 3 sentences which he will generate, which may not be similar to my sentences, because human has a different understanding of the words. When I'm speaking certain word, you understand uh, is there any volunteer I can tell you with something, maybe some experiment we can perform? Is there any volunteer who is present? Hello, guys.
Yes, ma'am.
Okay, so if I tell you to tell me a very beautiful word other than the beautiful, what word you will tell? Only one word? Any word which is come in your mind randomly. I don't want any.
Gorgeous, ma'am.
Okay. Any other person who will volunteer?
Illegal.
Yeah, any other word?
Natural beauty.
Yeah, thank you. So the thing is that many times which happened is that when we talk about certain words, and if I tell you, if I ask third person, it may be a synonymous word which other two people have said. So if you have seen, the first person took a time. The thing is that because it was a first time, and a beautiful word is a kind of an adverb. It's not also a noun. So she must be thinking, if I say happy, that maybe it may be little easier, but beautiful is a little odd word. Okay, so she must have thinking that, okay, awesome, matlab kya bolu, there must be 2 3 word which come, and then one word he has pick up. The second person, because he must have started with the earlier one word, he may have some idea in the brain, and then he may have come up with the word. So words has its own understanding, which we ourselves don't know. Like for example, I give one more example, is that the moment when I say the word magic, okay, something come on our mind. But when I say a black magic, okay, again some different connotation come in we call in the natural language processing. So what I'm trying to tell you is that the words are a very dicey things for the processing. And what has happened with LLM is that LLM has come up with a mechanism where it obviously it perform a mathematical operation. We are going to see that mathematical operation, which we called as a attention. So it what it does, rather than capturing each and every words which the person is talking or which is the inputting, it will only consider the important word based upon its the previous understanding. Okay, because it has its own history of RNN, which is a sequential processing. Okay, so because of this particular magic, LLM can generate the output. So you have to understand, LLM generate the output only few important keywords which are present in the input. It doesn't consider all the word at a time. obviously it considers certain range. So at a time it considers certain window, like the way LLMs are growing, like GPT-1, GPT-2, GPT-3, GPT-5. It is, we call as, it's solving a some problem called as a long range dependency. मतलब क्या है कि how much previously it can go. Okay, when we are solving a Rubik's cube, human has a ability कि अगर 15 class चल रहा है तो first class का it will automatically map. Okay, we any dumb student will also map if he pays little attention. Okay, that human brain is capable, but earlier the our models were not capable. So now models are little bit getting capability based upon the operation called as the attention mechanism. Obviously, there are many. The whole architecture of LLM is there. There are different layer. Transformer has its own architecture. There are different architecture, like only encoder architecture, only decoder architecture, unidirect, like GPT is a one directional architecture, rather Google Bird is bi-directional architecture. So it has its own understanding, but obviously it has its inculcate side effect, which we called as a hallucination. That means that because it is not taking the exact everything which is there in your input, it will take a 10 instance, it will produce 5 instance. Matlab, if I give a question of suppose 15 words, it will generate a 50 word from the 15 words. Okay, based upon its training, obviously, but still it may possible that in those 50 word there must be some hallucination. Also, it depending upon the input word. मतलब अगर मैंने कुछ input दिया और suppose अनघा मैम ने कुछ input दिया, even though there are few words are same, okay, but your output will change. Why? Because depending upon the way the input is given, the way which model you are using, the way the sequence is given, and so on and so forth. Okay, so LLM is a big jump for us as an AI engineer, and it was a very difficult problem earlier with the textual data. Now lot of textual data. Now if you can see all the people PPT or report or everything, there is a lot of text. Okay, so in the whole thing, what we essentially do is that we take an input, we tokenize it, we embed it, and then we give it to some model, and then based upon that model, it will generate some kind of output. Where we are going at something called as a reasoning. Okay, so LLM अभी तक रीजनिंग कंपोनेंट ज्यादा नहीं करता है, एंड एक्सप्लिसिटली स्पेशो टेम्परल रीजनिंग तो बहुत ही बैड करता है. लाइक फॉर एग्जांपल, yesterday I tried to create a map for LLM evolution from the GPT. It has given me the textually proper geographical location, but it didn't give me a proper map. So always maps or temporal or spatial location wise agar trajectory, if you are trying to reason, it will not give you the properly. Okay, so but the thing is that now because of LLM we can integrate a textual processing with our standard image processing. That means that I can write a query to the satellite image. Okay, I can write the query or I can give a elastic query. मतलब मैं natural language में लिख सकती हूँ कि find the villages within 2 kilometers of the blood, something like that. So that means that I can give a natural query. Your LLM will convert it in terms of a Google Earth Engine query, and then it can give you the output. So the beauty of it is that we can combine two things together, which was not possible earlier. Okay, I still remember 2012 and 13, me and Suryakant was discussing the Elasticsearch, that we wanted a system where we wanted to, I mean, the farmer should write in his own language, and the decision support system should give, what crop, what fertilizer, how to give water to a particular plant, what should be the frequency, and all these things can be retrieved. So technically, it was not possible in 2012 and 14, but now it is possible. Rather, there are many apps are there. There are many big companies are there, which those are doing this thing, and it is now possible. Okay. The next thing where we are going at, and it is not very popular with the geospatial domain, and frankly speaking, I also haven't worked a lot with this, but I was involved in last year with one of the project with Professor Durba, where there is a company called as, there is a body which we called as a OGC, which standardize the geospatial standards, and now they wanted to come up with a platform. I think I will share with Anaga ma'am, there are new platforms are now coming where we can directly write a query and then it will go to multiple sources and it will give you the data. Like earlier we used to go to USGS website, or we had to go to Google Earth Engine, and then we have to write the script, JavaScript, and it will give you data. Now data, you can write down the Python script and it will go to multiple website. It will integrate together and it will give you the output. These things are also available with the OGC support. So, but the thing is that these are still on a lower level. We wanted to come up with the higher level of all these things where we can multiple processing capacities will come together for solving one single task. Okay, and this particular thing which we are calling is called as a agentic AI. So we wanted to integrate the various geospatial tools such as a Google Earth Engine, Quantum GIS, LLM. It will analyze, all the tasks which are data analysis, data processing, which is MLDL, and the deployment. And from deployment, even checking what is going wrong and fixing by itself is something called as a agentic AI, which is specifically for multi-step processing with respect to a particular problem statement. Now, the problem is that with the geospatial domain, it is why I told you that agentic AI is not very popular with the geospatial domain. Still now, maybe 2025-26 में बहुत कुछ हुआ रहेगा. I haven't gone through with the detail of that. But because geospatial domain data characteristic itself is a multi-scale, okay, itself is a multi-temporal. मतलब क्या है कि अगर मुझे suppose I have a problem statement where I just wanted to monitor the air pollution. तो guys understand that air pollution का खुद का season है. जैसे for example in India we have a 3 season. एयर पोल्यूशन का विंडो जो है, डेली वेदर चेंज का विंडो इंडिया का, मॉर्निंग, आफ्टरनून, इवनिंग, नाइट ऑल्सो डिवाइडेड इनटू टू स्पैन. ओके, मल्टीपल लोकेशंस प्रेजेंट है. तो अगर मुझे एक एयर पोल्यूशन का अगर पोल्यूशन बढ़ जाता है तो अलर्ट देना है, तो उसके लिए मुझे मल्टीपल यूनिट्स हैज टू बी एट मल्टीपल टाइम हैज टू गेट मॉनिटर. तो उसको मॉनिटर भी करना है, उसको अलग अलग स्केल पे भी रखना है, उसके अलग अलग विंडो में भी रखना है, अलग अलग लोकेशन का डेटा भी इंटीग्रेट करना है, उसको एट अ टाइम एनालाइज भी करना है, और उसके हिसाब से मुझे आउटपुट भी देना है. Okay, so technically now in 2025 it is possible. Earlier it was not. In the larger scale, it was not possible. Okay, obviously, IMD was giving alert earlier also using mobile, SMS, but now it can give in a more refined way, and that more refined way is a kind of a agentic AI, where you are autonomous. Different geospatial agents that can plan, act, and improve the current situation. Okay, so this is what agentic AI where we are going at. Another thing which is which has gained a popularity, which was my ma'am, as I told you, my PhD topic was on something called as the ontologies, and now it has a very nice name called as a symbolic AI. Okay, so earlier it was as I told you कि गूगल किसी का मानता नहीं है. गूगल is a multinational company and it has its own whole dominance in explicitly the area of natural language processing. So Google has also come up with a different word for ontology, that is we called as a knowledge graph. So it is a kind of a similar kind of a technology only, but as I told you, it was a little different than the traditional model based system. Model based मतलब हम लोग जो मैथमेटिकल डेटा ड्रिवन सिस्टम पे एमएल पे काम करते हैं, जहां पे वी टेक अ डेटा एंड वी बिलीव दैट कि वॉट एवर डेटा हैज गिवन इज द ओनली अल्टीमेट ट्रुथ. ओके, which is not actually right. So as per AI philosophy, I don't want to go in detail about that, but we have something called as a different types of human has a different types of I don't know what to word use, processing or a method by which it makes sense. Okay, what I mean by that is that कि अगर if you want to understand any particular thing, we have a different one of the mechanism is a distributional semantic. मतलब क्या है कि multiple units होते हैं there, but and those multiple units come together and we feel that okay, this is this, like maybe a gut feeling. Most of the time we cannot give a reason, but most of the time the reason is given, this is the maximum time occurring phenomena, so this is the good thing. Like student do that कि बाबा paper में rather than understanding the subject, they solve something called as a PYQ. PYQ is the previous year question, क्योंकि subject का breadth बहुत ज्यादा होता है and we know that कि अगर ये question इतने बार पूछा गया तो next time उसका occurring phenomena ज्यादा है. तो ये जो बेसिक अंडरस्टैंडिंग है, दिस इज व्हाट आवर एमएल एंड डीएल का फिलोसॉफी है कि बाबा डेटा में जो भी मैक्सिमम टाइम अपीयर्ड है उसी को हम लोग ग्राउंड ट्रूथ और उसी को मीनिंग बताएंगे और उसी के ऊपर वी गिव आउटपुट. बट देयर आर अनदर फिलोसॉफिकल वेज वेयर वी से दैट कि नो, the meaning is not related to only the distribution, it also related to connotation and denotation and its history. Okay, and the logic behind it. Okay, we start from Plato and many philosophers are there. So though from those there is some mathematical theories has come, like as I told you, the logic based theory, predicate logic, preposition logic. From those theory which AI scientists have translated in terms of a mathematics, and those AI kind of AI we called as a symbolic AI. I don't know whether I have make any sense to you or not. It is little different thing. Okay, so symbolic AI में I'm really sorry ये change नहीं किया है मैंने. Symbolic AI में we use a different we use LLMs, we use knowledge graph, we use ontologies. Those are basically a mechanism specifically for a memory. ओके तो ये एक टाइप की मेमोरी है जो मेमोरी, बिकॉज ह्यूमन यूज डिफरेंट टाइप्स ऑफ अ मेमोरी. वन ऑफ द मेमोरी ह्यूमन यूज अ कनेक्टेड फॉर्म एंड दैट कनेक्टेड फॉर्म इज अ सिंबॉलिक एआई विच स्पेसिफिकली यूज फॉर स्पेसिफिक रीजनिंग एंड द इन्फरेंस कैपेसिटी. ओके, लेकिन ये इसका बहुत ही कंसेप्चुअल अंडरस्टैंडिंग है. Okay, all these models which we are talking about a machine learning and computer science where machine can understand only mathematics. Okay, it doesn't understand ये जो मैंने इतना कुछ आगे पीछे बोला. So obviously whatever concepts are there has to get translated into mathematical formulation so that machine can actually use it or actually use it for the processing. Okay, so इसका सबके पीछे जो बेसिक मैजिक है वो मैथमेटिक्स ही है. ओके, यू हैव टू अंडरस्टैंड दैट कि एलएलएम भी जो काम करता है और जीपीटी जो भी आता है, जो मैं अटेंशन मैकेनिज्म बोल रही हूँ, ये एक मैथमेटिकल फॉर्मुलेशन है. ओके, अगर उसका मैथमेटिकल फॉर्मुलेशन नहीं आता तो जीपीटी भी नहीं आता. तो होल मैजिक बिहाइंड सीन इज द मैथमेटिक्स. तो लेट अस सी कि ये जो सारे मॉडल्स है, इस मॉडल के पीछे बेसिक मैथमेटिक्स क्या है एंड हाउ दिस बेसिक मैथमेटिक्स एक्चुअली अफेक्ट योर आवर मॉडल्स. तो द फर्स्ट कंपोनेंट जो है वो है मशीन लर्निंग. तो मशीन लर्निंग में क्या होता है कि वी हैव सर्टेन फीचर्स, आई मीन वी हैव सब इनपुट x1 to xn, and then we create a mathematical function on it, and based upon this mathematical function, and then there will be some process. तो जैसे svm है तो ये svm परफॉर्म करेगा इसके ऊपर, अगर xgboost है तो xgboost परफॉर्म करेगा. तो इस इनपुट के ऊपर we extract the feature, that feature we give it to the some model, and model will give you some kind of output which is here represented as a y hat. ओके तो x मेरा फीचर वेक्टर है, x शायद मेरा आयत फीचर है, जैसे क्रॉप monitoring में NDVI, okay, is my one of the features. So many features are there. Those features are represented by vector. In that vector, there is some bias term which get add, and then we apply some classification algorithm, okay, and then we predict some kind of output. So any kind of output which, if it is a regression problem, it will generate the some kind of a mathematical number. Okay, तो ये मेरा basic formulation है machine learning के लिए. ओके मेरा डीप लर्निंग के लिए अगर स्पेसिफिकली अगर CNN या यूनिट है, तो व्हाट आई हैव इज आई हैव अ इनपुट इमेज. I'm going to first perform a mathematical operator which is called as a convolution. After the convolution, I'm going to apply some kernel offset with some activation function, or with some hidden layer, with some a kind of optimization function, and I'm also going to manage something called as a loss. Okay, and then I'm going to perform some kind of a iteration to get the output. So DL basically learn directly from the image and directly predict the pixel classes. Okay, जहाँ पे CNN specifically use होता है classification के लिए, और unit specifically use होता है segmentation के लिए. नाउ जनरेटिव एआई में अभी, बिकॉज जनरेटिव एआई का फॉर्मुलेशन हर एक इसमें अलग अलग है, बट ज्ञान में वी डू हैव अ टू डिफरेंट डीप लर्निंग नेटवर्क्स, जनरेटर नेटवर्क एंड डिस्क्रिमिनेटर नेटवर्क. सो व्हाट डू वी डू इज दैट वी टेक we formulate a problem as an optimization problem, okay, where we want to generate an image which is more realistic. Okay, so generator will generate the some kind of image. Discriminator will check that particular image till the iteration is been performed. So यहाँ पे we have a generator network, we have a discriminator network, we have a X as an input sample, there is a Z as a random noise which is get generated. We are trying to generate the expectation of actually log likelihood expectation of both images which we are generating. So we are generating the real image and we are generating a fake image, and then we try to noise and unnoise the image until certain optimal point is been met. Okay, so if I want to clear a clear image, my GZ is the cloud free and highest resolution image which I am trying to generate. Okay, we have a large language model, जहाँ पे large language model में we have a input as a token, क्योंकि large language model में all input which are given we called it as a token. Token का length जो है वो अलग अलग हो सकता है, मतलब token could be one word input, it could be multi word input also. Okay, then we convert those token into some embedding vectors or embedding matrix, and then we perform something called as a attention mechanism. तो attention mechanism जो है उसका एक फॉर्मूला है जो बेस्ड होता है क्वेरी वैल्यू. क्वेरी एक की होता है और एक वैल्यू मैट्रिक्सेस होता है, उसके ऊपर देन वी परफॉर्म सम मैथमेटिकल ऑपरेशन ऑन दोज क्वेरी इनपुट एंड द डेटा which is get matched with the training data, and then we perform a kind of a deep learning based processing using a traditional activation function, hidden state and everything which will be there. Okay, and then we are trying to generate the sequence of output which we called as a language modeling. Basically large language modeling जो है वो language modeling से आया हुआ है. Language modeling का मतलब क्या है कि we give a input as a certain word and we try to predict the next word. तो यहाँ पे भी large language model में we take a input as a query. Already there is some embedding because it is a already trained model, so it get matched with some values. There is some key which are present, and based upon that it will generate certain kind of a tokens, and those tokens will be given as an output. Okay, so attention mechanism, attention formulation is a very important formulation with respect to a large language model. Now, when we go towards agentic AI, what is changing is that because multiple units or a programming processing units are coming together to give or to perform a certain task. तो अभी इसमें एक जो मोस्ट इम्पोर्टेंट एआई का AI का method is been very essential is called as a reinforcement learning and optimization. तो इसीलिए यहाँ पे policy, because in agentic AI multiple agents are coming together and it has to generate a sequence of action. ओके तो वो सीक्वेंस ऑफ एक्शन जनरेट करने के लिए आई एम गोइंग टू फॉर्मुलेट दिस प्रॉब्लम एज अ ऑप्टिमाइजेशन प्रॉब्लम वेयर I need to synchronize in a such a way that each time it will select a best policy at each step, and you have to select the best policy by giving something called as a reward at a particular time, and that reward mechanism we called as a reinforcement learning. Okay, it is okay if you don't understand. Just remember that कि agentic AI में the reinforcement learning and optimization is important because multiple units are coming together. Why multiple units are coming together? Because agentic AI is supposed to perform action. It's supposed to also, for performing action, it's supposed to select certain tools or certain things using some probability and using something called as a memory. Okay, so it will first plan, then it will fetch, it will run, it will compare, and then it will give some kind of alert. Okay, so ये agentic AI का basic ये है. Rather than symbolic AI का, symbolic AI, as I told you, it is a specifically reasoning component. Reasoning component मतलब you wanted to give a multiple constraint together. You want to perform certain action, but you want to say, no, okay, if this is also fine, if this is also fine, if this is also fine, then it's okay. Then that is okay. Like for example, maybe it is not a related example, but when the person is getting married, he may have a multiple constraint, saying that my partner should be this, then my partner should be that, my partner should be that. He should be at least this and that. Okay, so this kind of a constraint, if you want to put on a certain item while performing the action, then we use something called as a symbolic AI. Because symbolic AI mein we can perform a various rule-based techniques. Okay, and we can also perform something called as an inference. Inference का मतलब क्या है? Because we can connect multiple unit at a time. From one unit, we can directly move to or the next unit. ओके तो ये जो मल्टी स्टेप आउटपुट है दैट वी कैन यूज अ सिंबॉलिक एआई फॉर इट. लाइक फॉर एग्जांपल, अगर मुझे फ्लड, अगर बारिश हो रही है तो बारिश में अगर इफ वाटर लॉगिंग इज देयर, देन इफ वाटर लॉगिंग अगर अबाउ इस स्पेसिफिक टाइम के ऊपर जाता है, देन आई नीड टू परफॉर्म द सेट ऑफ एक्शंस. Okay, synchronously. Now in this particular case I can use a symbolic AI rather than algorithmic AI, जहाँ पे machine learning और traditional DL based जो model है वो एक certain type का ही output देते हैं, certain format में ही देते हैं. Rather symbolic AI में that binding is not there, but it is not a very heavy data driven processing. Okay, so what exactly we are looking at is, we have till now look at is the deep learning, generative AI, LLM, agentic AI and symbolic AI. तो अभी deep learning में like we have a CNN, we have a auto. Am I on the right track?
Yes, ma'am. Yes, ma'am.
Yeah. So deep learning में basic key technologies are CNN, MLP, and that is autoencoder, so on and so forth. Specifically उसका key feature है कि वो hierarchical feature learning है. We don't need to give the feature, we don't need to perform a specific operation to extract the features. It is specifically solving a layered by layered. जनरेटिव एआई में जैसे ज्ञान है, VAE है, डिफ्यूजन मॉडल है. स्पेसिफिकली इट इज यूज फॉर जनरेटिंग अ न्यू पैटर्न. ओके, LLMs बेसिकली ट्रांसफॉर्मर बेस्ड आर्किटेक्चर है. मेजर 2 आर्किटेक्चर है. अभी देर आर few more architecture in the market, but जो basic है वो GPT and BERT है. Basically task होता है कि how you can generate the next token. एजेंटिक एआई में एलएलएम है, टूल्स है, प्लानिंग है, मल्टीपल टाइप्स ऑफ एजेंट है, बेसिकली प्लान, एक्ट एंड फीडबैक लूप है. सिंबॉलिक एआई में नॉलेज ग्राफ है, रूल्स है, लॉजिक है, एंड सो ऑन एंड सो फोर्थ. So can anybody answer this? Which AI generation first enable the automatic feature learning from the satellite imagery? Okay. So the answer is a deep learning. So we will just take one use case. Like this is one of the SIH project which we got. So we will just see with this use case how we can apply this multiple method. So the problem was that the trees which are near to close to high voltage power line can create a problem. And for that, the tree height has to be managed. Okay. Now in this case, what in the previous session which I showed you, what we did is that we took a satellite data, and from that satellite data we have just measured something called as a NDVI, and we have monitored the NDVI. What is NDVI? NDVI is the indices which is represent for a green color. So agar green color and the height of a tree and the texture, if we take a three feature and if we perform some kind of a classification whether tree height is high, medium, low, okay, then we can give a output. So this is the way ML can apply. Rather deep learning, agar if you want to apply, what we can do is that we can take the images, we can directly give those images to DL. Now DL will automatically classify without performing any indices based operation. जैसे वहां पे we took a image, we calculate those indices, मतलब we manually calculate those indices. Those manual calculation from computer is going to be avoided using deep learning, because deep learning will create its own feature map. Okay. Now, if I want to use a generative AI in this, then what I can do is that because we know that ki baba, generally we have to take a satellite data, but the best data is my LiDAR data. Okay, why? Because LiDAR can give you more detailed data, specifically with respect to creeper or any other activity. Big trees, it's easy. Satellite also can can give you the good visibility from satellite you will get. But from smaller plants, which also goes around the power line, also have its own fire hazard. Okay, so for those kind of a problem, if I need a LiDAR data, then a LiDAR data will be very costly, because the power lines in all across the India, and it is very difficult to get it's very difficult to put that much cost to get a LiDAR data. So what we can do is that we can, as I told you, we can have certain patches where we can create a LiDAR, we can take a LiDAR images, and then we can synthetically generate for other region LiDAR images in order to find out the kind of a fallen trees or any other damage or anything like that. Okay, so because generative AI is capable of generating the new images, we can actually find out those missing data using generative AI. Now what LLM can do? Now LLM can write direct report. Okay, where the storm has happened, where the tree has fallen specifically. LLM also can have a kind of a communicator where the person can directly talk to LLM for getting the output in terms of a textual format. Okay, obviously the basic disadvantage is that many times, LLM can hallucinate. So if you are using LLM, you require a grounding mechanism, which we use the word. Now, specifically with respect to geospatial domain, you require a geospatial grounding mechanism. Okay, we need to specifically have something called as a careful prompting mechanism. We can also have a agentic AI in this particular problem statement, where we can actually generate the path for LiDAR data, for UAV path, which can optimize and can give you the, can give you the a data, because as I told you, the LiDAR data or UAV data is very costly data. Okay, so there are certain risk zones are there. Like for example, near the airport or some critical infrastructure, there will be always some risk zone. So in this, by avoiding those risk zone, we can use agentic AI to generate the plan for getting this kind of a data. Okay, symbolic AI can be used for connecting multiple entities together. Okay, to give a some kind of a semantic reasoning. ओके तो ये मेरा ये सारा इतने सारे टाइप्स ऑफ एआई हो गए, इतना सब कुछ हो गया. इसमें अगेन देर आर वन मोर कॉम्प्लिकेटेड लेयर विच आई वांट टू ऐड. इट्स कॉल्ड एज specifically when we talk about ML pipeline or a DL pipeline, we generally have two perspectives. Okay, at least from the computer science perspective, there are two perspectives. One is the model centric perspective and one is a data centric perspective. तो हमारा जो बेसिक लाइफ साइकिल होता है कोई भी एआई प्रॉब्लम का, वी हैव अ प्रॉब्लम डेफिनेशन, वी हैव अ डेटा प्री प्रोसेसिंग, देन वी हैव अ मॉडल ट्रेनिंग, देन वी हैव अ मॉडल टेस्टिंग, एंड देन वी हैव अ इवैल्यूएशन एंड डिप्लॉयमेंट. लेकिन इन ऑल दिस थिंग विच पार्ट हैज टू गेट मोर इम्पोर्टेंस? ओके, लाइक इन प्रॉब्लम डेफिनेशन में वी हैव टू अंडरस्टैंड दैट कि बाबा कौन सा मॉडल यूज करना है फॉर विच डेटा टाइप. तो मॉडल सेंट्रिक एंड डेटा सेंट्रिक में, मॉडल सेंट्रिक इज मीन विच आर्किटेक्चर, वेदर डीप लर्निंग, एमएल, एजेंटिक एआई, एलएलएम, which has to be used. Okay, data centric में what type of data I required. Okay, I wanted to talk little bit about sampling, but I don't have time today to talk about sampling, because the sampling play very significant role with respect to data driven systems. Because the thing is that in geospatial domain, we by default we have two samples requirement. One is the location sampling and one is a time stamp sampling. तो टाइम सैम्पलिंग का भी एक खुद का एक विंडो होता है एंड लोकेशन का भी एक खुद का विंडो होता है, बट प्रॉब्लम इज दैट कि वी नेवर गेट दैट डेटा बेस्ड अपॉन दैट विंडो एंड बेस्ड अपॉन दैट टाइम लोकेशन. मतलब वॉट एवर डेटा विच आई हैव वर्कड विद, आई नेवर गेट एक्चुअली वेल क्यूरेटेड डेटा. मतलब इफ आई एम डूइंग सॉइल फर्टिलिटी एनालिसिस इन कोल्हापुर रीजन, तो for few villages I may get lot of data, for few villages I will not get data. Okay, for few villages I will get data, but I'm thinking that this data is not proper. Okay, so the thing is that for any ML or DL problem specifically, we need a proper data, then only we can have a proper output. But obviously the models are also very significant. So model centering में, how do we improve the model? In geospatial term, you assume the data is limited, it is imperfect, you push the model architecture harder, you can use lot of variations, CNN, transformer, specifically we talk about hyperparameter tuning. Okay, so model centric AI, geospatial domain में मतलब we are improving the algorithm based upon the complex pattern which are available in the real world. Rather, in data-centric AI में, how do we improve the data? So how we can fix the label, okay? How we can reduce the noise, how we can increase the diversity, how we can curate the data to get a specifically spatial and temporal coverage. जैसे मैंने बोला, आज तक in my whole years of 15 years of my experience in geospatial domain, I never get data which is spatio-temporally proper covered data. At least it is a real-time data. Okay, so this is the path which we have went through from last 45 minutes. We started with kind of a ML, which is specifically with respect to model centric, then DL, then Gen AI, then LLM, and then we have a agentic AI. Okay, so in ML, it is a model centric, it required a good feature. Okay, you required a more bigger model architecture to get more obviously architecture has to be bigger and data also has to be bigger for get a more pattern extraction. Generative AI में you required a proper representative data so that you will get a proper output. In LLM obviously can give, but it depending upon the model which we are using it. And agentic AI is basically depending upon the orchestration. Orchestration मतलब जो मल्टीपल एपीआई है और यूनिट है वो एक दूसरे से कैसे कम्युनिकेट कर रहे हैं is important. So in model centric, if your model is weak, it cannot handle the geography. If your data is wrong, the best CNN will also not going to give you the proper result. Okay, so model centric improve the learning capacity, data centric improve the geospatial truthfulness. We required a better data and better model. So obviously this is requirement, but many times we don't get it. Okay, so can anybody give me the answer for this? Why geospatial AI shift from model-centric ML to data-centric workflow? Okay, so the answer is B, because our data is diverse, noisy, and incomplete. Okay. So guys, now I'm going to go fast. It is just the introduction of why deep learning is very significant compared to ML, because in geospatial domain, we have a data which is large, which is complex, which is non-linear, which is rich in pixel. Okay, so more intricate feature if you want to extract, we require a deep learning. Basic difference in deep learning is that ki baba machine learning mein you have to extract the feature. Deep learning mein features are directly been extracted. Okay, so if the traditional machine learning, complex data pattern, feature engineering, lack of generality ke वजह से, we have to go for deep learning, for hierarchical feature learning, end-to-end learning, and adaptable learning. Okay, so deep learning is basically we take a input as input data, we perform a deep neural network, and we get the output. Okay, we have a 3 basic unit: input layer, hidden layer, and output layer. Okay, so there are different types of deep learning network. Like we have for CNN, then we have a RNN, we have a LSTM, we have a GRU, and then we have a lot of different variation of deep neural network. Okay, so can anybody answer this? Deep learning become necessary geospatial analysis because high dimensional spatial pattern, and there are many raw data imagery which is present. So this also from 2020 to 2025, I have extracted few references and I have performed कि बाबा deep learning में कितने geospatial domain के publication हुए. So if you see it, it has been increasing from from 2021 itself. Maximum जो domain है जिसके ऊपर सबसे ज्यादा research हुआ है वो land cover और landslide and flood disaster के ऊपर सबसे ज्यादा domain है. दिस इज एब्स्ट्रैक्ट के बेसिस पे वर्ड क्लाउड है. सो सबसे ज्यादा डोमिनेंस ऑप्टिकल डेटा विद सीएनएन है, मल्टीस्पेक्ट्रल डेटा विद यूनिट ज्यादा है, सार डेटा के साथ सीएनएन यूनिट ज्यादा है, डीएम डेटा के साथ रैंडम फॉरेस्ट ज्यादा है, और लाइडार के साथ भी सीएनएन ही ज्यादा है. Okay, so these are few case study of my student which I just wanted to, if somebody is interested, we can connect later. Okay, so this is very very popular plant leaf detection जिसके ऊपर we have a field crop, we have a leaf data, then we use CNN for it, and traditional CNN algorithm is being applied. Okay, then this is automated slum classification using deep convolution network. तो इसमें we have taken, this is a this year project. So what we did is that इसका एक so we took a data from Google Earth Engine GeoTIFF image, and if you know Google Earth Engine ka data is not that is good resolution data, and we are not getting good result actually for this. The problem is that because specifically in Bombay region, Dharavi slum is very very uh, 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 some areas are very small, some areas are very big. So it is very difficult to automatically classify it. So what we did is that we took a TIF image, then we have done feature engineering, and then we created the tentative labels because the Google Earth Engine ka data label data nahi tha. So then we perform a traditional k-means algorithm, and then we perform a sample labeling, and then with the human we have generated the labels, and then that is given to the CNN model, and then it is been visualized using a traditional accuracy and the arc in the traditional way. Okay, so the thing is that I think our results, if you see, yeah. So our results are not comparatively that good compared to the other people result, but it is still a good problem statement, and it is the most difficult problem statement. So this is also one of the problem statement in which we have worked, a land cover land use classification for the hyperspectral images. Okay, so what we did is that now in this case also initially we wanted to train the hyperspectral data using the GPU, but the problem is that in my college we were not able to use the GPU. So ultimately what we did is that we apply PCA on it. We converted into the RGB space, and then we have applied kind of a data pre-processing. So we have performed 1D, 2D, 3D kind of a CNN, and on this 1D, 2D kind of 3D CNN, we have performed, before performing this, we have applied the PCA. Okay, so these are our 1D, 2D, 3D ka ye. This is a benchmark data set available on IEEE port. Okay, as this is a well curated data, if you can see, the accuracy is quite good. Now, obviously, we have applied PCA on it. PCA means we have converted hyperspectral image into the RGB images. So ideally, it should not give us a good result because we have lost all the spectral data of hyperspectral. But as this is a well curated data, it's a Kansas region data from USA, it is giving a good result. Okay. So then we have generative AI. So generative AI is referred to artificial intelligence, which can create the content. So generative AI is a subset of machine learning, which can specifically which can specifically generate a kind of output. Okay, so we don't have time. So in generative AI, we have specifically 4 models, prominently transformer-based, generative adversarial network, variation autoencoder, and multimodal model. Okay, so as we don't have the data, we don't have the time. This is also one of the problem statement which we have used and we presented in GRASS, which is where we have used GAN for cropped prediction. Now, if you know that cropped prediction is a very significant thing, but the thing is that many times we don't have a data. So we have 12 different states ka data which was available. Some of the data, actually main data has been taken from data.gov, but for all the region data is not available. And for that purpose, what we did is that we use a GAN, okay, to generate the synthetic data, and then we have performed the kind of a crop yield prediction. So complex and non-linear correlation make difficult for GAN. The problem is that because India is a very diverse country, all the 12 states have a completely different feature space. Many times GAN was not able to give a proper output, because if you think GAN will also get at one point of a time, it will suffer from certain problem. One of the problem is a mode collapse problem, because there is a lot of variance and skewness available in the data. Okay, so this is one of the synthetic data creation which we have used. For synthetic data creation, generally we use TSNE and all those parameters for evaluation. This is, again, as I told you, this was a SIH project which we were working on, high voltage power line, which they have implemented. So in this case, we have collected the data from I think Google Earth Engine only, and we have used different types of indices. One of the indices is NDVI, NDWI, Then we have used the indices called as a CVI, which is Canopy Vegetation Index. We have also used one of the so Landsat 8 and band, different band which we have used from Google Earth Engine only, EVI data. Again, we have used LST data, and then we have used AGBD data. These all indices has been calculated from Google Earth Engine. We have calculated the data from 2020 to 2022, and using this particular data, we have applied something called as I think LSTM they have applied. Yeah, so data study area, satellite, Landsat 8, Moody's, and AGBD cover, and from the power line weekly data, which we got it from power line only. And then on that, we have applied LSTM layer to get the output. So LSTM can little bit remember the long-term trend and the seasonal pattern also, and so that we can monitor the vegetation growth. So the problem is formulated as a time series remote sensing problem, where we wanted to identify the risk zone for the power line, which are near to the certain tree, and the output is generated in terms of a risk score. Okay, and the model which has been used is a LSTM model. So we have taken the data from Google Earth Engine, then LSTM, then we have trained and tested you on LSTM. It has been evaluated using RMSE and MAE, and then we have one web app where we are showing that kind of output. तो ये इसका ये है. So this is one of the app or a website which we have created where it will generate the risk factor for a particular region. Okay, so this is what a kind of the deep learning based and generative AI based project which we have worked on. Another thing is the LLM based kind of a project. As I told you, I haven't worked till now a full-fledged on the agentic AI, but I have worked with something called as a geospatial RAG. Okay, so geospatial RAG is something called as a geospatial retrieval augmented generation. We don't have time now to discuss this thing in detail. If somebody is interested, they can connect me on LinkedIn. So what happened with the traditional LLM mechanism is that we have the whole bunch of data which has been trained on certain language model or a large language model, which we called as a GPT and all those things. So it do have a global context. मतलब अगर कोई चैट जीपीटी यूज करता है तो ही मे हैव ऑब्जर्व दैट कि मेनी टाइम जो भी आउटपुट आता है वो इन यूएस स्पेसिफिक या यूके स्पेसिफिक ज्यादा आता है कंपेयर टू इंडिया स्पेसिफिक. ओके, व्हाई? बिकॉज द डेटा फॉर द यूएस इज रिप्रेजेंटेड मोर. सो देयर इज अ प्रॉब्लम विद ट्रेडिशनल लार्ज लैंग्वेज मॉडल विथ रिस्पेक्ट टू ग्लोबल स्कोप. लेकिन जैसे जियो स्पेशल डोमेन में लोकल स्कोप इज वेरी इंपॉर्टेंट. कि जैसे लोकल स्कोप में बोला जैसे बॉम्बे का अलग है, पूना का अलग है. तो अगर आप if you are working in a domain where certain areas are important and then with respect to that you wanted to give a output, जैसे मैंने बोला कि फार्मर अगर एक क्लिक करेगा और उसको अगर आपको आउटपुट देना है, तो इंडिया के फार्मर में जलगांव का फार्मर एंड कोल्हापुर का फार्मर आर completely different because their crops are different, their geography is different, their weather patterns are different. So if you wanted to even give an output in terms of a text, but the text, it will be very difficult with the traditional GPTs or LLMs which are available because they generally work with the global context. तो अगर आपको local context में work करना है, तो there is a one special technique which we use called as a RAG. तो RAG is another word, technical term में हम लोग बोलते हैं grounding mechanism. Grounding mechanism because LLM hallucinate मतलब it generates something which it's supposed to not generate. Okay, so you will take a local data and you will retrain certain LLM so that you can give more priority to the local data than your global data. So this is very popular with respect to geospatial domain. Okay, as I told you कि special context और special geography, local geography generally हमेशा dominate करती है. Okay, so this is like you want to perform something called as a geo chat Okay, but for this geo chat, you are going to use something called as a geospatial RAG. तो geospatial RAG में क्या होगा कि you are going to take you are going to give a question with respect to object, location, and relation. Then input is going to be match, image is going to be retrieval is going to be performed, image label is going to be performed, and then it will give you the some kind of output. Okay, if you don't understand at this moment, all this thing is okay. Only remember that with respect to the RAG also, geospatial variations are available. Obviously, every domain has its own variation. अगर आप healthcare में जाते हो तो healthcare का भी खुद का RAG अलग होता है, because वहाँ पे you require more precise information in healthcare. Okay, with respect to the human population in that particular specific group. Rather, in geospatial domain, the location and the time, okay, is a very significant thing when you are giving any kind of a output. Even in geospatial domain, many times the output has to be in terms of an image or in terms of a map. Okay, which till now LLMs are not giving, but maybe in course of time LLM may give kind of the output of a geospatial maps. आई हैव सीन कि जो इसरो का इस बार रिस्पॉन्स आया था उसमें देर इज अ जियो स्पेशल एलएलएम के ऊपर 2-3 प्रॉब्लम स्टेटमेंट थे. तो मतलब द थिंग इज दैट कि इट इज रियली कमिंग इन द मार्केट. Okay, so we have a different we required image and text together with respect to the traditional with respect to geospatial RAG compared to a traditional RAG which works only on a text. Okay, so guys, as I told you, maybe the today's session will be little cognitive overload session, because I started with ML, then we went towards a DL, then we went towards a generative AI, then we went towards a agentic AI, and also discussed few part of a symbolic AI. Okay, so basically ML is a kind of a mechanism or data processing capacity which try to understand the patterns from the data. In deep learning, it will learn the structured pattern or deep pattern. Generative AI, it will actually create the pattern. Agentic AI is act on the pattern. Symbolic AI can give you the logic behind the patterns. Okay, and then we have seen multiple case study. There are multiple things which are happening in geospatial domain. Rather, from last 2 to 3 year, technology is evolving very fast. Okay, but the thing is that it is okay to be whatever you have understood. You be with your problem, be try to understand, interpret whatever you are studying and learning. That is only the way to go ahead. Okay, so that's it from my side.
Thank you so much, ma'am. The floor is open for questions. So, dear participants, if you have any questions, you can share your questions here. You can unmute yourself. You can ask your questions. Yeah, ma'am, we have a question from a participant. Is symbolic AI able to handle all types of data like raster data, vector data?
So symbolic AI is, yeah, it can have the one line answer is yes. Second line answer is symbolic AI is a human generated data based upon the data which is present. So obviously it is up to the human who can interpret the data and generate knowledge graph and ontologies and metadata. If you want to automatically create a symbolic AI system, which we called as a learning component, like it will automatically learn the patterns, then we use the traditional mechanism like deep learning and generative AI only. So I hope I have answered the question.
Yes, ma'am. Any other questions from the participant? Okay.
Ma'am, there is a one question is there. For deep learning, we have the TensorFlow, PyTorch library. So do you have any libraries for the symbolic AI? Hello, am I audible?
Yeah. So we do have a library, but the thing is that symbolic AI के लिए the more popular platform is a Java platform compared to the Python platform. Okay, because in NLP domain, the Java was the earlier, the technology. So we do have a wrappers which are available for the Python. So if you want to study, because it's a little complicated domain, I haven't touched it much, but the file format which we use in symbolic AI is RDF, OWL, and SWRL rule. If you want to follow that domain, there are two flagship conference. One is ESWC, another one is ISWC. There is a two working group. One is IOA. It is open. It is not paid kind of a platform. So you can go to Semantic Web Journal or IOA platform. There the papers are present, so you can understand it better way.
Ma'am, we have next question from the participant. What ethical challenges arise when deploying generative AI for content creation?
Oh, it's a it's a very debatable question. So I know that there are, as I told you, I was a part of a OGC. So there are regulatory bodies which are coming, and I think in your session only the security aspect has been covered. So it's a big challenge. That's the one line answer which I can give you. And specifically with respect to the era of war now, it's a very, very big challenge that people can manipulate the information by generating the content. Okay, so I think the security aspects is been already covered in certain session. I don't think so I should touch that in detail, but yes, there are ethical concerns, but there are no protocol specifically, and SOPs are I know certain bodies are there who are now coming up with strongly with these protocol and SOPs, but till now there is no standard document, at least I have seen.
Thank you, ma'am.
Hello. Good afternoon, ma'am.
Yeah.
I just wanted to ask whether we can fuse SAR optical LiDAR data in real time and deploy our systems effectively. Is it possible to have the multimodal data?
If it is a LiDAR data, then how it is a multimodal data? It will be the
No, if
traditional.
all the if we are going to fuse the SAR and optical and LiDAR data in real time, is it possible?
Yeah, I mean, theoretically, it is possible because the thing is that SAR, LiDAR, and optical, all three data will be geosynchronized data as per my understanding, right? Or nowadays, we do have the different fusion mechanism because specifically with talking with respect to fusion, what we need to do is that we need to fuse the data based upon spatial and temporal footprint. मतलब क्या है कि जिस लोकेशन का वो डेटा है और जिस टाइम जोन का डेटा है उसी के ऊपर उसको मैप करना है विद द लेयर. So you can have optical data, you can have a LiDAR data, you can have a SAR data. I haven't presented one of the problem statement which we are trying to work now is a woman safety zone prediction. तो जैसे वहां पे डे टाइम में ऑप्टिकल का डेटा लेना है, सम सार का भी डेटा लेना है, एंड सम पार्ट ऑफ द डेटा विच इज बिकॉज इल्यूमिनेशन का भी डेटा लेना है. So you can fuse the data based upon its time, location, and with respect to the locations which are available. But then how you are going to use it and what will be the file format and what will be how it is going to be managed, it is up to you. Like for example, I don't want to create an image. I'm going to create an indices. I'm going to store it either in a CSV format for one particular location at a one particular window, which will be the equally distributed, or I can have a JSON file also. So I hope I have answered your question. So it is possible.
Okay, ma'am. Thank you. And ma'am, one more question I had. Actually, we have learned about few short learning models. So, will it work on this geospatial data also? We have studied about transfer learning and deep learning all over in this FDP, but few shot learning, is it possible to use on geospatial data? Where very few samples are present for training, and then you get the
Okay, so look, the few shot learning is specifically use the term with respect to the transformer model. मतलब
yes,
GPT के साथ या LLM के साथ उसका ज्यादा word का use होता है. But if you are but whatever you are telling me based upon that, whatever my understanding is that you have a sample data which is a less data, and
yes,
from that data you want to predict something. Okay,
yes.
and that is why you are using the word transfer learning and all those things. So the thing is that कि yes, obviously there are different names which we use. Like for example, अगर 2010, 12, 15 के पास आप हो तो मैं बताऊंगी कि उसको हम लोग सेमी सुपरवाइज एंड ट्रांसफर लर्निंग वर्ड यूज करते थे कि हमारे पास फ्यू सैंपल अवेलेबल है और उस फ्यू सैंपल से आई एम गोइंग टू अंडरस्टैंड, आई एम गोइंग टू ट्रांसफर इट टू द अदर डोमेन एंड आई विल ट्राई टू अंडरस्टैंड इट. और आई कैन हैव अ सेमी सुपरवाइज, जैसे मैंने असलम डिटेक्शन का किया कि मेरे पास लेबल ही नहीं है. ओके, एंड आई हैव ओनली फ्यू एरिया जिसको मुझे जनरलाइज करना है. सो व्हाट आई एम गोइंग टू डू, आई एम गोइंग टू फर्स्ट परफॉर्म द क्लस्टरिंग. ओके, आई एम गोइंग टू बेस्ड अपॉन क्लस्टरिंग आई विल फाइंड आउट सिमिलर ऑब्जेक्ट. पहले मैं उसको लेबल करूंगी, बाद में लेबल 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 करते जाऊंगी एंड देन आई विल अप्लाई द क्लासिफिकेशन एल्गोरिथम. दिस इज ऑल्सो वेरी ओल्ड मैकेनिज्म विच वी कॉल्ड एज अ बूटस्ट्रैपिंग. मतलब ये पहले भी अवेलेबल था जिसको हम लोग सेमी सुपरवाइज बोलते थे. अभी चैट जीपीटी में या ट्रांसफॉर्मर्स बेस्ड मॉडल में हम लोग फ्यू शॉर्ट लर्निंग का मतलब क्या बोलते हैं कि वी विल टेल देम, क्योंकि वी कैन डिवाइड अवर इनपुट इन टर्म्स ऑफ अ स्ट्रक्चर्ड फॉर्मेट विच वी कॉल्ड एज अ प्रॉम्प्ट. तो प्रॉम्प्ट को हम लोग बता देंगे कि बाबा ये टास्क परफॉर्म करना है, लेकिन ये टास्क परफॉर्म करने के लिए यू एनालाइज द पैटर्न बेस्ड अपॉन दिस सैंपल फर्स्ट, यू एक्सट्रैक्ट द पैटर्न एंड यू अप्लाई इट. ओके, तो टास्क वही है, करना वही है, पर उसका मॉडल जैसे चेंज होता है वैसे उसका प्रोसेसिंग चेंज होता है. जैसे हमने भी, मैंने बोला कि ज्ञान के यूज किया, तो ज्ञान में क्या किया कि बिकॉज डेटा वॉज नॉट अवेलेबल, आई हैव गिवन फ्यू सैंपल टू ज्ञान, आई हैव क्रिएटेड फ्यू, सिंथेटिकली क्रिएटेड फ्यू मोर सैंपल्स, ओके, फॉर क्रॉपेड, एंड देन आई हैव परफॉर्म द क्लासिफिकेशन. तो वो वही है. मतलब आई होप इट्स द
Oh,
सेम थिंग
oh,
व्हिच यू आर आस्किंग.
okay, okay. Thank you so much, ma'am.
Thank you so much, ma'am. And yeah, so here we are concluding the session for today. Thank you, ma'am. On behalf of AP Shah Institute of Technology and the Department of Data Science CSE, the organizing committee and all the participants, we extend our sincere gratitude to you, ma'am, for delivering such an amazing session. Your deep expertise, ma'am, the clarity of explanation and the way you took us into the understanding of the evolution from ML to symbolic AI, along with the mathematics behind and the case studies, the real-time projects, has really given us a very great insight, and it has inspired us to explore new research direction and applications in geospatial analytics and to keep learning, ma'am. Thank you so much for your valuable contribution and making this session so impactful. Thank you, ma'am.
Thank you for the opportunity.
Thank you, ma'am. Thank you so much.
So, yeah. So now we are moving to the next session. Just a minute. Okay, before moving to the next session, if you can see the feedback link and the attendance link on the chat box, so requesting you all to fill it for the session which has been completed right now. Okay, so it's my privilege to introduce our distinguished speaker, Dr. Suryakant Ashok Sawant. Dr. Sawant is a scientist in the Digital Food Initiative Division at Tata Consultancy Services, Pune. He holds a PhD in Geoinformatics and Natural Resource Engineering from the prestigious Indian Institute of Technology, Bombay. Currently, Dr. Sawant leads the DFI Sky Remote Sensing Research Team, where he is responsible for driving innovative research and implementing advanced remote sensing solutions for agricultural applications. With over 14 years of combined industry and academic experience, including more than 7 years at TCS, he has made significant contribution to the field of Earth observation. Dr. Sawant has an impressive research portfolio with 15 patents filed, 5 of which has been granted, and more than 35 publications in reputed international forums. His works extensively utilizes multispectral, hyperspectral, and synthetic aperture radar SAR data for agriculture insights. He has contributed to diverse applications such as canopy nutrient estimation, soil moisture assessment, crop variety identification, pesticide residue analysis, and pest and disease detection. He is also a life member of ISRS and the Indian Society of Geomatics. In addition to his research, Dr. Sawant has conducted numerous workshops in IoT and sensor web technology for weather monitoring and crop water management. His key areas of expertise include remote sensing of vegetation, IoT and sensor web for agriculture water management, GIS, satellite image processing, and AI application in agriculture and forestry. We extend a warm welcome to you, sir, Dr. Suryakant Sawant, sir, who will be delivering today's talk on geospatial technologies for smart and sustainable agriculture. We are grateful for your presence and looking forward to your valuable insight. We are truly honored to have you, sir. Welcome once again. Thank you.
Yeah, thank you. Thank you for the nice introduction. I hope I am audible.
Yes, sir, you're audible.
I will share my screen. Let me know when the screen is visible. And just for the information, I have 2 displays, so maybe I'll be looking up many a times. So it may appear that. Is my screen visible now?
Yes, sir, it's visible.
Yeah. So I'm on the slide 1. I'm presenting my introduction. Like here, the topic is mainly on the geospatial technologies for smart and sustainable agriculture. So when we say smart and sustainable agriculture, it doesn't completely align with the approach that we are taking in. So I would call it rather regenerative agriculture these days, because the smart and sustainable may not be the appropriate word. So regenerative is my preference. And today in this presentation, what I will be covering is the combination of 3 major sectors: the agriculture sciences, the geospatial sciences, and the computer science, for applying this in the core agriculture related problems. So what I will do is I will give you very clear picture from the basics of remote sensing till generative AI and AI related advancements that are happening. And I would just like to tell that the whatever knowledge that I am sharing today in terms of AI and generative AI is around 1.5 to 2 months old. So when I say 1.5 or 2 months old, is like this generative AI and AI things are changing very fast. So what we will be doing is I'll be covering all the basics, because I think the audience here is very from different domains, and they may not be having the understanding of what is remote sensing, what is time series, what is vegetation greening and browning and all that. So I will give you first this introduction, and then I will go into the details of certain use cases that we had developed and certain projects that we completed in the research. So overall, the coverage will be starting from basics of remote sensing till the application of this geospatial AI, and concluding with the advances and challenges in the geospatial foundation models. So what is the pixel? So this is the remote sensing basics, like we may call it as remote sensing 101. So when there is a satellite, you see the satellite which is there, the atmosphere of which is collecting the data set from very far away, around 700 to 600 kilometers away from Earth. The light which is coming from sun, solar radiation, is reflected from multiple features or multiple aspects that are present on the ground, which is in terms of vegetation and other aspects. And that reflected light is being collected. This is a typical example of optical satellite data set. So when this light reaches the satellite sensor, it collects the data and it sends it to the ground station. And it will look something like this. So each of the pixels. So what is the pixel here is each of the pixel will have its own dimension, which is like a ground resolution. So it can change based on the sensor that is we are looking at. So it will comprise the image or the data that is collected will comprise of multiple sensors, which will be present in the multiple pixels, which will be present in the data set. So when we look into the remote sensing observation, we mainly look into 4 resolutions. So talking first is the spatial resolution. Spatial is about how large is the pixel. Is it 10-meter pixel, 20-meter pixel, or 100-meter pixel? Its size is basically dependent on the number that we are mentioning here. If it is a 1 meter or less than 1 meter, is the size of pixel. So the Google satellite data that you use for the maps, the base maps, these are around 0.2 meter resolution, like around 20 meter resolution. And certain satellite data providers, they also provide data set in 2 meter, 1 meter, and 3 meter resolution. So the open source data set that is available, Sentinel-2, Landsat, MODIS, these are around 10 meter, 20 meter, 30 meter resolution. And then coming to the other resolution is the radiometric resolution. Radiometry is nothing but if a pixel is there, like the complex level we are putting the data set or we are storing the data set. Like, are we recording this data of this pixel in 8-bit integer format? So if we are recording this data in 8-bit integer format, it will take typically values between 0 to 255. And if we are recording this pixels data in different 16-bit format, it will go into 0 to 65,000 odd number, gray values. So this means that whether it is a red region, near infrared region, or any other region, the radiometry also plays an important role. So radiometry tells about how well-defined segregation is there within the reflected light that has been captured by the sensor. If it is 8-bit, very less information, 16-bit, very high information that you can very easily interpret. Coming to the third resolution is the temporal resolution. Temporal resolution will tell you from day 0. So if you consider this time t 0, 5, 10, 15, 20 is like a days, how many days the satellite data or the pixel data is available? Like this sensor, if you look below, this sensor is providing you data after every 5 days. There is another sensor. When I call sensor, it can also be a satellite. So satellite like Sentinel-2 or Sentinel-1. So it provides the data after every 10 days. So that a pixel is again repeated after every 10 days. So you can typically construct a time series. In the next slide, I will be telling you about how to construct a time series. But before that, there is a last resolution that I would like to tell is the spectral resolution. So spectral resolution is nothing but how many spectral regions are being covered in this data set. So this is the 8-band multispectral data set that you can see typically Landsat or Sentinel-2 will have. And there is a 3-band RGB data set. Like our mobile phone cameras, there are certain very high resolution panchromatic and the multispectral sensors which collect the data in the 3 bands. And mostly for vegetation applications, we use 3-band plus near infrared. That is totally the 4-band data set that we use. And as in introduction, it was provided, I mainly work in the vegetation monitoring part, and that too specifically into agriculture and the forest vegetation. So here, how the story of time series is coming up. So the pixel that you've seen before in the first slide, it was about the image that was collected by one sensor at one point in time. Now, suppose that sensor is collecting data set, or there are multiple other sensors which are similar to that. It is collecting the data over multiple time periods. We can construct the time series. And the time series may look something like this. So it is like time t0, t1, t2 till tn. This is the time series of a 1 pixel. So like that, multiple pixels will have a large amount of data set, which you can construct in terms of time series data set. And then you can apply multiple functions which are related to time series analysis. So typically giving a realistic view here, how the crop will look like in different stages. This is the crop at TCS Digital Food Initiatives farm. We call it as a demo farm or a digital farm, where it is just a half-acre field where we plant different crops, different season, and we collect the satellite data set around entire season. And then we also validate our algorithms, which are satellite-based algorithms, computer vision algorithms. So coming here, providing a view is just after planting, how the field looks like. after emergence how field looks like. You cannot directly see the plants that are there, but this is the corn crop. Corn means like maize crop, which is growing up, which is for fodder maize. So now the early vegetative phase, you can see the NDVI has increased, the early vegetative phase. And there was certain stress condition because of which the NDVI has gone down. And that time you can observe there are certain things that may be happening. But right now I don't have picture for that. But here the representative picture shows at a very high vigor of the vegetation. So vegetation, when it has grown, it shows the vigor of the vegetation that is grown over the particular stage. And then now you see on that particular date, different time period, there is an additional vegetation that has grown. So, but there was no satellite data available. So you can see the dots which are showing you on the satellite pass. If there is a gap, that means there was certain issue that for that farm, we don't have the data. But because we had a time series extracted for that particular farm, and this is aggregated time series view, which shows that somewhere around NDVI will be in this range at this point in time. And then the harvest phase, when the crop is going under the complete drying phase or the harvest phase, this is the vegetation index it will look like. So in remote sensing of vegetation, when you look into agriculture aspect, this kind of ground truthing is always being preferred by research community and for model creation, because until and unless there is no ground truth data set, your papers or the publications may not be accepted in the high impact journal factors or high impact journals, because their impact factor or their reviewers will definitely ask about what is the ground truth data collected, how intensely it was collected, and how specific you are talking about your application or the findings that are there. So that is the important part that comes in play. And I just wanted to give you a view. Those which are students right now listening to this talk, they may understand it, the importance of field data collection or the field presence. Coming to similar analogy, like when you look into the crop, like here the greening and browning, when we say greening and browning is nothing but the crop starts greening, it is like a growing stage, and then there is a senescence phase. Senescence phase is nothing but the crop is about to get harvest and it is mature. So in crops, it will look something like this. So for seasonal crops, it will look something like this. So this is the corn crop growing from the seed till the harvest phase. And this is the typical vegetation. This is the deciduous vegetation where the forest initial canopy is there, then the leaves are not there. So the vegetation is dropping. It is not dropping to zero. There is certain reason why it will not drop to zero, because there will be other plants also, the bushes or any grass that will be present on the ground. So I'm not representing it right now, just for simplicity. So, or it is like oversimplified view of this greening and browning. And again, there will be a greening during the spring. Similar way, there will be time series applications that you can generate for multiple such vegetation types and use them for certain applications. So we'll be talking about these applications in upcoming time. So what are the applications here to identifying the cropping systems when the crop was planted and how many crops were planted. So if the bank is interested in knowing when the crop was planted by a farmer who has taken loan or has taken the insurance in that given geography, then it can be useful to understand when that loan was when that crop was planted and it was harvested, how many crops were planted, that is like cropping intensity, and what was the gap between two crops. Similar way, what are the regenerative agriculture practices that has been followed for this planting or crop planting. And then coming to the vegetation which is related to forest, whether it is what type of forest it is. So if it is agroforestry systems, you can easily understand that whether it is a deciduous forest or it is an evergreen forest, or it is like a temperate forest where there is a complete cover of snow at some point in time. So this kind of assessments can be done very easily by not directly going into the field every place, but by taking representative observations. So this is the typical example, and this example will be again coming in our slide at some later point in time. So right now what I'm showing is here the actual scenario which was deployed for a particular customer. Customer is actually a potato chip or potato wafers manufacturing company who is actually interested in knowing what is the stage of potato crop. This is large in US or European geography. where they would like to know how the variation in the potato is happening, whether the ground cover is increasing as per their expectation, and is this potato being harvested. And in addition to this harvesting of potato, they would like to also understand that whether the farmer is going for some regenerative agriculture practices or not. And what are those regenerative agriculture practices? I'll be talking in the subsequent part. But before going to that, I will show you how this also can be used for irrigation management. So irrigation management here, you see, there are multiple phases that are there in the soil that are covered here in the bottom portion, where A, B, C, D. This shows that variation in the water levels in the soil. And then there is a regular increase in the decrease because of the addition of water. So this is like a typical irrigation cycle and input output of the irrigation management part. But our story was still here, where we are looking into the vegetation growth and the regenerative agriculture practices. And similarly, in the irrigation sector also, there is understanding that is required to optimize the water, because when we come to regenerative agriculture practices, regenerative is for all the resources: soil, water, vegetation, and we have to optimize all these parameters, not only one, because in intensive cultivation, we have seen that because we have only focused on the yield increase, there is an environmental impact that was created by these activities or the activities that are performed on the field. Because of excessive application of fertilizers, the leaching of fertilizer went to the other water streams, and the pollution started increasing in the other water streams, and then water got polluted. So the holistic approach is required, and that's why the irrigation also comes in play, and why the irrigation management and how to do it is the one part that also needs to be looked into agricultural systems. Then coming to regenerative agriculture practices, as I was saying, what are those? Like the cover cropping or the field cover understanding is the one part. The other part is crop rotation. Then there is an option of tillage that is going for the minimum tillage. Then the mixed cropping. And why this regenerative agriculture practices, as I was trying to give some motivation around that part, is the climate change is impacting our food production system, where this system is already being stressed because of increasing the population and the increasing the demand for the food production. And the regenerative agriculture practices are also needed to conserve our microbiome. So microbiome that is dependent on the agriculture, and the after agriculture, whatever is coming out of the field, which is going to the natural streams like rivers and other water streams like the small water streams, those are also getting impacted because of whatever is happening in agriculture. If there are certain pesticides that are being applied that are very harmful for the fish, they are impacting the fish production in the larger water bodies, because that particular fertilizer or pesticide is flowing into the natural systems. It is not just staying within the soil that is being where they are applied. And I am talking about open cultivation. So I'm not talking about anything about the closed cultivation. Closed cultivation is nothing but the greenhouse or the cultivation which has a controlled environment under some cover. Then there is also a need of digital measurement, reporting, and verification. So measurement is nothing but understand and measure how much is the thing being done. Like, for example, how much tillage is being done, whether it is intensive tillage or whether it is minimal tillage, and then apply the things according to that and provide the benefits to the end users based on the measurements. Reportings are for the regulations like governments and these things, and verifications are nothing but the evidence-based funding. Like verification mechanisms are there where the standard organizations are coming in play, like Vera standards are there for carbon stock assessment. Gold standard also has the few standards. So these parts we'll be discussing in subsequent slides, a few more about certain regulations that have come up in recent days, and how these regulations related solution can be generated using the satellite data. So those solutions also we'll be talking about. So coming to the crop cover or cover crop. So what I will do is I will just take a pause and would like to take feedback from maybe organizers and others, like, is my voice audible and clear?
Yes,
And
yes.
is this okay? If there are any questions, I think you are open to put your questions in the chat window so that I can read and I can respond also on the go, because I can read both the things simultaneously, on screen and also the chat window. So we'll continue on our discussion. So our discussion was around how to monitor the regenerative agriculture practices using geospatial technologies. Until now, what we have covered is the basics of remote sensing, starting from the pixel of the satellite data till time series generation. And then we looked into certain aspects of regenerative agriculture practices that can be monitored using satellite data. There are multiple such operations that you can monitor. And now we are at a slide which is showing you the cover crop. So cover crop is nothing but once I have planted my main crop is here the corn crop that you see on the ground here. And this crop is harvested at certain point in time. Now my field is going to be barren if I don't apply a cover crop. Cover crop is nothing but a crop which is going to cover the field during the time when there is no main crop that is being cultivated. And it can also be planted when the main crop is about to harvest. So when this is like going in browning phase, then also the seeds can be sown in this field. And when just after harvest, this crop will come up. So similarly, with using the satellite data, what we have done is for that customer, we identified for a given date of estimate. Like for example, a farmer was onboarded on a date, this line, which is around 2022, somewhere in the time. Then what we did was we extracted the historical satellite data. So around 1 to 1.5 years of historical satellite data was extracted. And we provided the view of how much was the duration when the vegetation was present on the field, for how much duration there was a main crop present. Main crop means the corn or whatever crop that a farmer has planted. Then how much was the duration? Because this is a temperate climate, northern latitudes around US and Europe geography. How much duration was the snow present on the ground? So for Indian geographies, you might have not seen snow unless you go to northern states like Jammu and Kashmir, where apples are grown. But some other regions in the northern latitudes like US and other regions, there is a snow cover also for significant amount of time, around 2 to 3 months, the snow cover is there. So how much is the duration of snow in that fields and how much is the duration of the cover crop? So that was also important part to understand that whether the farmer has gone for cover cropping or not. And if the cover cropping is being done, that means the soil conservation activity is being done and the nutrients, additional nutrients or the soil organic carbon is not disturbed in the soil. So coming to the seasonality part. So if you see typically Indian subcontinent, starting from north of India till the south, far south, in Tamil Nadu and Kerala, you can see such kind of vegetation patterns in agriculture systems. And these patterns are nothing but how many crops are being grown. So for starting from June, like typical monsoon season cropping system, where onset of monsoon, we start planting our crop and the crop grows. The first planting we do it start of the season is started and the cropping season ends around somewhere in the October. And October to December here in typical Punjab and Haryana geography, where rice and wheat ecosystem is there. The wheat is rice is harvested and now they are preparing land for the wheat. And when you see the pollution in Delhi, unfortunately also contributed by a certain part of Punjab and Haryana because of some stubble burning. And stubble is coming from nothing but the rice cultivation. And this burning part and the management part of stubble is a major aspect there. So the fallow period is very short in this geography. So this typical fallow period of 1 month I have shown is actually a kind of a simplification. But these farmers, they are getting only 10 to 15 days within which they have to take the stubble out. That rice stubble or residue that has been left has to be taken out and they have to do something about that. So machinery and the availability of such kind of mechanisms are not well placed. They are poorly placed. And because of that, they are actually has to go for the burning. Burning is the easiest option. And they go for the burning and then the pollution related issues, they come up and the farmers are being considered as a culprit for the pollution that is causing in Delhi. But in Delhi, the pollution is also caused by some other reasons also. The industrialization and the other aspects, construction activities and the smoke from other industries, that is also there. Also vehicular pollution is there. So we also already have published a paper during COVID times. What happened is agriculture was working, but the most of the transportation and other pollutants were not there. So what we did was, it was an interesting case. We tried to see during this period, is there a contribution of smoke causing the pollution in Delhi or not? But you can read that paper and understand. It is available as a link in my Google Scholar profile, or I may also give a link. So interestingly, it shows that agriculture is very less contributor. to that particular pollution that is being caused in Delhi. And because the vehicles and other pollutants are not there in the environment, the pollution levels are less. But again, without diverting into that aspect, I am showing here typically the time series of 2 cropping systems. So I will be further complicating this by adding certain monitoring aspects into this when there is a tillage that comes in play. So basically, tillage is nothing but the soil management practice where the equipment is used, like tractor and the moldboard plows or multiple other harrowing instruments are used to invert the soil and prepare it for the seedbed preparation. So in intensive tillage mechanisms or tillage kind of a systems, what happens is there are multiple passes of tillage. After planting, also there is an interculturing tillage operation where the weeds are being killed by doing this kind of operation. It is not intensively done, but the tillage before the planting and after the harvest is the intensive tillage that they follow. But whether the farmer is following this kind of tillage activity or not is also can be monitored using the satellite data, and where minimal tillage scenario can be seen, like the farmers who are going for minimal tillage, that they can get certain benefits or certain incentives, and that can be monitored using the satellite data or time series of satellite data. And that we did. And similarly, in the geographies like temperate regions, when they are cultivating the crop, which is one cropping system. So you may not be knowing the temperate climates like US and European geographies, they cultivate only one crop in a season, either winter wheat or the spring wheat. So they don't go for 2 crops because their environment itself is not suitable for cultivating multiple crops. But short duration multiple crops they can cultivate. Initially, they cultivate the spring short duration fodder crop, and then they go for the potato or maybe wheat crop. So it depends upon the region, like whether it is Germany or it is France or whether it is US geography, northern latitudes like Michigan or other areas. So coming to the tillage or minimum tillage, this minimum tillage is nothing but very few passes of machine in the ground to cover the soil or to invert the soil and prepare it for the seed or planting in the next season. And why this operation is being done is like typically in some of the areas there is also issue of forming the hard pan or hard surface layer, which is obstruction for the seed to grow. So that's why some farmers also go for the tillage operations in India geography. But in northern latitudes, the soil organic content is a bit higher. In Canadian geography, soil organic content is around 3% to 4% in certain places, and it ranges between 1 to 3% soil organic carbon. But in India, if you see, the soil organic carbon is around in agricultural systems is less than 1% in almost entire country. In the forest areas is around 2 to 3% soil organic carbon. So that way we have impacted the environment and the soil systems in our geography. So basically what we are doing is in TCS, we develop our algorithms around this kind of non-invasive interpretations or mechanisms to interpret the operations that farmer is doing and then provide the insights for a given fields. So now we'll move into the next aspect. As last speaker was also mentioning about the current trends in geospatial AI and AI, and these AI related aspects are coming up in mainstream. So before going to this part, I would just like to take questions. I think they are there. Which vegetation indices beyond NDVI or NIR are proving most effective for early disease prediction in diverse Indian crops? So this question I will answer maybe in the last part, because these are specifically indices or the part that you are asking for the pest and disease may not be the right now topic of that particular vegetation monitoring, and the spectral bands that are most sensitive for the soil disturbance. So I will take this question. Spectral bands that are most sensitive to the soil disturbance are the shortwave infrared. SWIR bands are there. As we seen, near infrared and shortwave infrared regions are also there. So if you use NDTI, normalized difference tillage index, so is the one of the index that has been put forth by researchers, which is used for the soil disturbance. And also synthetic aperture radar. So synthetic aperture radar is nothing but it is a structural data set. So structural means it tells about the geometry of the field. So synthetic aperture radar is actually providing you a VVVH, vertical polarization, vertical reception, vertical polarization and horizontal reception. So this kind of VVVH backscatter can be replicated and identified into surface disturbance in terms of coherence, and that interferometric SAR or the backscatter itself can be interpreted for the understanding of surface characteristics like surface moisture, surface inversion, or surface disturbance, etc. So these are the two aspects. Yeah, another question is like how satellite, drone, and IoT sensor data can be integrated into unified geospatial platform for real-time farm monitoring. So that also the question I will be answering in the end, because that part is I just wanted to give some view into these geospatial AI and AI related advancements. And as I said before, this is around 1.5 months to 2 months back kind of a assessment that I have put in the slide. So the changes I will be putting up maybe in upcoming days. So here, why there is a need of this AI actually in agriculture, the geospatial domain. So in geospatial domain, as you may be understanding over these lectures or FDP program, integrating the geospatial data is very difficult. And there is a baseline that is required. The domain level baseline data sets are required that are not there. So I think these are the aspects where we need the geospatial foundation models. And the pace of collecting these geospatial observations has increased multifold. That means today, the data set is being collected at a rate at which we cannot interpret it. So there is a huge amount of data is being collected on day-to-day basis by multiple satellites, but our capability to interpret those data set has really not grown up to that extent. So there is a Sentinel-2, Sentinel-1, Landsat, MODIS, then multiple other ISRO satellites are there, but all these data sets are not getting interpreted for the applications that are there for vegetation or agriculture applications. So certain satellite data sets are interpreted for the weather data sets. So weather satellites are different. I'm talking about here Earth observation satellites. And the other part is the domain-based foundation models. Like there are foundation models you might have not seen, or some of you might have already got exposed to. There are also atmospheric sciences, solar sciences, and the solar flare related models are created by NASA and IBM, joint collaboration, and also Google and IBM and Google and NASA in collaborative efforts. So similar way, maybe we may not be in the position right now to afford that amount of compute, but at least we can use those models or the available embeddings in our modeling frameworks and make a use of this kind of understanding that has been created. So that is the objective in telling about these AI-related advancements right now. So benchmark and AI-ready data sets are also an upcoming challenge for India geography, at least, because our data sets are being distributed and they are available in silos. We need to have a unified framework to connect all these data silos and collect the collective advantage of that particular data set for land records or other aspects. So as maybe a very basic slide for many of you, you may be all of computer science students. I am not computer science student, but I just wanted to give this view of foundation models. So when there is a foundation model, already definition you know, but I just want to highlight is that domain-centric foundation models are not LLMs. These are not LLMs that are there. They are different kind of models. LLMs are a different kind of models. LLMs are mainly for languages. The foundation models, when we talk about, and domain-centric foundation models, they are different. They take their embeddings in a different format. They have their own encryption, decryption mechanisms. They have their own aspects of similar to LLMs. There are downstream tasks. So they have their own downstream tasks. So some examples I'll be showing in the next few slides. And what is the geospatial foundation model? So geospatial foundation models, you may be knowing, there is a Prithvi 2 model by IBM and NASA they have created. And Google is also looking from Alpha Earth foundation models. So Alpha Earth foundation models by Google, they are geospatial foundation models trained using very high or very large amount of geospatial data, imagery from the satellites, maps, radar data, and also some of the models are also using the weather data sets. So weather data sets in a geospatial format that they have used there. So I'll not go detail raster formats and vector. Am I audible now? Hello.
Yes, sir.
Am I audible?
Now you're audible, sir. In between, there was a little bit.
Sorry, there was some disturbance.
Yeah,
I hope,
now it's clear, sir.
yeah. So I will continue. So what I will do is I will go into the next part. So this, if you see the literature and the advancements that are happening in the LLMs, so you see that LLMs have evolved a very a rapid pace, and there are certain LLMs which are related to agriculture. The AgriGPT, AgriBert are there. So these are specifically looking for language-related aspects of agriculture. So geospatial foundation models, if you see version numbers here, the Alpha or the Prithvi, they are 1 or 2 versions, but GPT has gone up to 5 or 6. So as I may be slide maybe still. Sorry, there was some disturbance. Am I audible?
Now
Yes,
we
sir.
can
Now
hear. In between, there was.
Yeah, I just to take a feedback. Is my voice audible?
Now it's audible, sir.
Yeah, sorry. Actually, there is again disturbance that is coming up. But the view here in this slide I wanted to give is around the foundation models or the research that is happening around the foundation models and the language models. So there are certain foundation models, as I was saying, the atmospheric foundation models, they are different than that of LLMs. The neural GCM, Aurora. So these are the models which are taking weather data sets itself in their basic analysis or basic processes, like initial data preparation and all that. Some of them are taking very huge amounts of what you call a baseline data set in terms of well-calibrated data set, when we call it with evidence, and the other data sets like here solar flare related model. So NASA and IBM together has formed the model heliophysics model, which is for solar weather. Like when there is a solar flare that comes out of sun, that impacts our satellite and communication system. So this model actually is the foundation model from NASA and IBM. So coming to this slide again, this slide I said will be coming up again. What does this figure means? Like what exactly this graph means, or what this raster map or image that tells, is actually very difficult to interpret unless there is a geospatial expert or there is a summary written by somebody with that much careful observation of these images. But doing that for multiple such fields and multiple such things is very difficult in doing in actual scenarios, because there can be thousands of fields that needs to be monitored. So why can't there be a LLM which will help us in interpreting this by having a RAG framework integrated with this data set and providing a context of this particular use case? Like this is the potato cultivation I talked about, and the potato cultivation is going under different phases. And when this kind of a knowledge we give it to that particular RAG pipeline, it can generate the very well contextualized or context specific textual summary telling about the story of this field, like how this field is performing and how overall its variations are, which are the regions in this field that are getting impacted, which are the regions that are not getting impacted, and what is the expected production, etc., in the well interpretable language, and what are the regions when the satellite data was not available, or where there was a very large amount of cloud cover was there, because cloud cover information is also being shown, and how it is impacting overall interpretation. That kind of actually assessment is required at this point in time, and further complicating it into multiple other aspects for client requirements. Yeah. Am I audible?
Now we can hear, sir. In
Yeah,
between.
whenever I'm not audible, please put me a message or maybe raise a hand, because that is difficult to know.
Okay, sir.
Okay.
Now you're.
Yeah, please. So in the last slide, what I explained was about why there is a need of LLM and integration of LLM. So was that clear? Hello?
Yes, sir.
Yeah. Okay. So going further detailed into this is like we had a pipeline data set where we were.
So again, the voice is fluctuating little. So
Sorry, again, I think there was some issue.
yeah. It was a fluctuation, sir.
Yeah. So what I was saying is we had a data processing pipeline set up, which was working on AWS environment and also other environments. Typically, 60 TBs of data set we were processing at every 10-day frequency, and we were generating multiple indices. But in that data processing pipeline, we found out there are certain limitations that were there, where vegetation indices we had to provide based on the use case specific requirements. Like for certain use case, we put the vegetation indices, and there was no integration with the other satellite-based indices, like the weather data sets and satellite database indices. Like weather data set like temperature, precipitation also has an impact on the certain signatures that we receive from the satellite, like NDVI or NDWI, which is water related index, or VVVH backscatter. So when there is a rainfall, the VV backscatter will reduce because the soil is getting moist, and it will get reduced, and it will show the moist condition. So these aspects are also covered using the weather data sets, like a rainfall or precipitation data set. And there is also very difficult to interpret the zonal statistics. Like calculation of zonal statistics is okay, but interpretation of the zonal statistics for a given field, if there is a mean NDVI of 0.7, what it exactly means for the potato versus what it exactly means for the rice is very domain specific understanding that needs to be interpreted. So that aspects we are actually missing, and that we are doing it right now using rule-based mechanisms. But with the help of RAG pipelines with LLMs, that got simplified for us. And what we did was we created an agentic AI framework to contextualize this kind of aspects for a field. And we generated kind of a RAG pipeline, which is like starting from user input till providing the report through this Flask API. This kind of architecture was created where user was submitting a region of interest in terms of polygon dataset, like field boundary, and the prompt parser, and user was also providing information to the prompt, like provide me the vegetation status or the health status of this particular field over the last 1 year. So what prompt parser was doing is it was providing the information to multiple agents in a sequential manner or in the parallel aspect. And what was happening is these agents were talking between each other with the local storage, and the orchestrator was handling this communication between each of the agent, where the status of agent is complete or incomplete. And certain agents were processing the data, like Google Earth Engine agent was processing the data set from Google Earth Engine and providing the output to the local storage. And local storage was accessible to everyone, for the report writing agent, for reasoning agent, for the data agent. And some of the agents, they were doing task of critique. So here reasoning agent was acting as a reasoning plus critique agent, which was doing the critique on the data set that is being generated by this GE agent for that particular field, whether it is right data, whether the cloud cover is present or not, or whether it is related to that particular crop or not. And reasoning agent was also taking a view of weather dataset, weather API it was accessing. And then finally, it was providing the input to this RAG report generating agent. So report generating agent, it had access to other information from other agents, which was collected as a kind of a data set, image, table, or a map. And finally, the PDF report was generated. And this entire interaction happened using the Flask or Web UI, the Flask API and the Web UI. So, and it was providing the output of PDF document. So PDF document had a view of a particular field and the details about that particular index, etc. So right now I'm not showing it, but I'll be showing other use case similar to this for the compliance mechanism, compliance monitoring mechanism. So this is one example. You can also think about such kind of architecture and implement it on with your own agentic AI framework. The other aspect was related to compliance. So when we go for the compliance assessment, so European Union recently has identified the deforestation regulation, and it was enacted from 2023. So June 2023, they started providing the information that the EUDR compliance will be active from January 2026. That means in the next month, this compliance mechanism will be in action for all of the companies or all of the people across globe, where some things when they are importing into Europe, they'll be looking for. So these some things are nothing but the cattle, cocoa, palm oil, rubber, soy, that is soybean, and the timber. So rubber is repeated here, but the timber is one part. So if there is an import of this particular material or particular ingredient in the European Union, they will look for where it has been originated and whether it was a deforested area from which it is originated. So it is called as a European Union deforestation regulation. So after 2020, if the particular land is undergoing into conversion from forest to agriculture, then they are demarcating as a deforestation, and it is a direct conversion of a field from forest to the coffee, soya, or cattle production, or the timber, and this is actually in effect. So they will call it as a deforestation, and the produce that is being coming from these farms will be rejected. So then there is an issue that which are the other aspects that will come in play. Whatever happening before 2020 or whatever has happened before 2020, they are not considering right now. So the forest that is cleared before 2020 and it is under agriculture, they are not classifying that as a deforestation. It has been classified as a deforestation, even though that is a risk where that is there, but they are unable to monitor it or they are unable to put restriction on it. So it is like a kind of a governance mechanism European Union has brought out. And then there is a second mechanism like forest conversion to degraded forest and then converting into agriculture. So this is a mechanism typically followed in certain aspects of India where encroachments happen in this way, like periphery of the forest, like in Mumbai or other. The forest region, when people try to intrude, they will create first the degraded forest. So some trees will be burned, some trees will be there alive, and then they will convert it into agriculture or maybe residential area, then that will lead to deforestation. So what will happen is, if anything that is coming of this nature, cattle, cocoa, palm oil, or timber or rubber into European Union, they will monitor for the source or origin of that from the particular importer and exporter. So if you look into supply chain, for example, for the coffee, so coffee cultivation starting from the coffees, beans that are collected, primary processing and the secondary processing that is happening, there is a export and import. So import is in European Union, but export is from other geographies. So at this point in time, the EUDR compliance will come in play. So when there is a compliance, there is a need of before even doing the import and export business, the logistic companies or the companies who are involved in this business, they will look into due diligence. So, and they have to submit this due diligence into traces system, EU traces. So what we'll do is the shipment, the number of shipments that they have, the quantity of shipment, whether there is 100 ton or 200 ton of coffee beans that are coming up. So their shipment has to be registered, and that shipment will be registered with the source from where it is coming up. And for that, geospatial technologies and understanding is required to map that source and identify whether that area is under risk or not. So what we did was we created an, again, agentic AI based architecture where this mechanism can be automated. So entire pipeline can be processed in terms of the agent based framework, where orchestrator will be looking into creation of due diligence report. So due diligence report is nothing but whether the particular field has undergone deforestation or not, and whether it is under risk or not. So there are multiple other aspects are there. The simplest part is the deforestation risk or the deforestation risk score. So there are multiple such agents. They are orchestrating different behavior, like reasoning agent, domain agent, like similar to the last example. And they are generating now the PDF of due diligence, where they will be providing the region of interest, the commodity of origin, whether the same commodity was planted on the field or not. Like, for example, certain suppliers will try to manipulate the system by providing the false information. Like different coffee plantation, they will be considering and providing the yield of maybe 1000 kg from that particular plantation. But based on the plantation size and the amount of production, average production that is there, it can be easily identified whether it is that much amount of production will come or not from that area. But other part is, suppose the owner is also different. Like one farmer is coffee grower who is a genuine coffee grower, but the supplier has tagged that same farmer multiple times. How to handle that? So such aspects also are being considered for the due diligence report. So that due diligence aspect will be handled using the blockchain and other technologies that are actually the peripheral technologies to store the data in a non-manipulative way. But this is the aspect for geospatial data assessments. So similarly, what we are doing in TCS is we are trying to create a kind of a agentic AI based models where multiple foundation models we are taking into play. So the process models are nothing but the crop growth models, crop simulation models. Then the geospatial foundation models, as I said, Alpha Arc Foundation model or the other Prithvi 2 or other models from IBM and NASA. And then the atmospheric foundation models, etc. So, and multimodal models, of course, they are there, and LLMs, large language models. So, as I said, two of these views I provided. One is remote monitoring and geospatial data interpretation. Similar way for the crop management practices, like what to grow, when to grow, how to grow, and then answering the question related to crop management practices, like which fertilizer to apply, what is the crop growth stage, etc. So such aspects right now we have this kind of agentic view also there, supported by multiple such models, and these agents can interact with each other, and it can benefit on three aspects: social, environmental, and business aspect, to multiple stakeholders. So this is the overall view or agentic AI vision that we have for our research area. And this is the overall layer of agentic AI that we have created, where multiple layers of infrastructure components, then the data set tools, and the agent to agent communication protocols, etc. are considered. So this may look like more information intensive slide. You may get the access to these slides or maybe video recording. You may refer it later. So infrastructure layer is the layer where your cloud compute will be hosted. So Google Cloud is the example I'm giving it. There can be AWS or Azure or any other cloud environment. Similarly, there will be protocol and agent and internet layer. So agent-to-agent communication, agent mesh network is there. Then there is a tooling and enrichment. So we, in our research group, we already have certain tools. So like irrigation decision support system, then there is a data analysis pipeline is there. But we call them as a tool. These tools are not intelligent tools unless there is a certain intelligence added to them. So that intelligence is added by certain foundation models and also certain reasoning mechanisms by language models, and they become then the agents and the information providers for the next layer. And then the memory and personalization, like memory and the handling and the reasoning and other aspects are there. And the governance is also there, like ethical guardrails and other aspects. The application layer, you already may be knowing about multiple layers of application like REST APIs, the prompt cleaners, and the prompt parsers. So basically, it is the terms that are coming from the prompt engineering domain, which was in the initiation of large language models and their use. So coming to the last two slides, the challenges in development of this kind of geospatial foundation models, the huge volume of data set, the compute cost, and the software cost is very high. And there is the issues of cyber security and also the physical security of certain aspects, like the information, some of the entities, they would not like to provide it for the public use. So this is the aspect on the technology and infrastructure side. Interoperability side, as you all may be appreciating it and knowing it, the information is available in silos. It is not available as a standard mechanisms. So as previous presenter was also showing, the Ujjwala ma'am was telling about OGC standards. So these standards are actually coming in handy for multiple agencies. And if you look at the European agency, like multiple European organizations, they are providing their datasets in all of the standard formats. Even the field level datasets are available in the standard formats. Other than the GDPR, like PII information, like very personalized information, the very basic information is also available from European Union for farmers, the farm ownership related details, but not specific to the personal identification. So, but the standards that they have used and the licensing mechanism that the European Union has used is an example for the globe to follow. So what they have done is all the satellite data sets, whenever a new satellite will get launched, it will be open source available across globe. So anyone can download it, and the license is Creative Commons license and the European Union license. So anyone can use it for commercial applications. So that kind of licensing mechanism is there, but that is absent in India for ISRO satellite datasets. Then the operational use, the field sizes in India, field sizes are small. You already know that, and certain other intercropping and other scenarios that are there, which are coming in play and that are creating issues for creating the baseline datasets for foundation models, like which are like supervised learning, initial supervised architecture that is there. For that, huge amount of baseline data sets are not available, but that needs to be created for India geography also. Agriculture universities have the data sets, but again, the first part and the second part comes in play, the interoperability of that and the data sharing and the hindrance in the data sharing that comes in play. Then the public policy around the cloud, like what is happening is there is a sovereign cloud and the cloud related local storage that is coming in play. So multiple agencies are being now asked to store the data in India geography already by Indian government. Similarly, that is happening in multiple other countries, and it is happening from last few years. And also there are some restrictions that are coming in terms of sharing the data sets which is not in their geography also. So that kind of restrictions are also creating an issue where there is a need of sovereign cloud being felt, and that is being actually worked out by certain companies in India also. And then coming to environmental and ethical aspects, like hallucination and other issues are there in geospatial models, the AI models. But in geospatial specifically, the GHG footprint of particular compute capability, that is also important, like how much GHG footprint is there and what is the data privacy laws that is going to cover. Then again, I talked about intellectual property and personally identifiable information. But after looking into the limitations, the scope is there for bringing something new to the table. Like for example, CPU-based models. There are certain LLMs that are like BitNet, which are like quantization-aware training mechanisms are there, which are actually trying to bring out the large language models to the CPU architectures. And the GPU-powered desktops are also coming up these days, which are actually will be helpful for using it for the small applications where very limited information is required and the generation of the small language models. So these small language models are going to be a future for some time, unless there is something new comes up. After every quarter or after every 2 months, there is something new that comes up. And of course, the interoperability related things are also happening. Agent to agent protocol is there. Like that, there are multiple other things are there, like embeddings. Embeddings in operational scenarios, the pixel-based time series and model embeddings that are coming up. I did not mention one of the model, geospatial foundation models, besides the Alpha foundation model, which is the Tesser model in the European Union. So their model is actually based on the time series. So what they are doing is they are reconstructing the pixel time series for the given geography. And based on that, they are creating the geospatial foundation model. So its exact name is Tessera. Tessera is the initiative by European Union for the geospatial foundation models, and it is a temporal embedding based model. So these kind of embedding and mechanisms, you may have to learn it better way besides the language models. So language models, tokenization, identifying the tokens and all the token similarity, other aspects, the matrices, then the vector database, vector datasets, the embedding creation and all that is different aspect. But here in geospatial, there is a different aspect, as Ujjwala ma'am was also hinting it in the last presentation. The data interpretation also is the very different aspect in this. Then, as I said, sovereign clouds are coming up. TCS is also working towards that. And CPU-based low-power applications like BitNet, etc., are coming up for environmental and better. So these are the few key references. In one of the slides, I showed all the numbers. We'll be maybe showing you this presentation in the sharing with you the presentation, so you can use this. And this is all we had for today. So I will take up now the specific questions and any comments that are there. Was it clear? Like,
Yes, sir.
hello, am I audible?
Yes, sir.
Yes, sir, you're
Okay.
audible, sir.
I hope it was clear.
Yes. Yes.
So one of the question is, what challenges do smallholder farmers face in adopting geospatial technologies? See, for smallholder farmers who are less than half an acre, geospatial technologies are right now not having the high resolution satellite data, like sub-meter resolution data sets are very costly. But the farmland itself is more than half acre or 1 acre or so. The monitoring aspects can be done, but certain data sets are actually locked in government data sets. Like for example, land records data set or other data sets in India geography. What is happening is if there is an insurance related product that has to be mapped for maybe any crop, like you take an example of groundnut crop or maybe rice or wheat. What happens is the data set is not openly available, and the farmer will get the satellite data set and the bank will be able to analyze that satellite data set, but they will not be able to understand what was the produce that was there from that region. So the government mechanism that is already existing on the village level, the sub-district level, that is taluka and state level, that needs to be strengthened by adopting certain mechanisms to open up these data silos from the government side itself, like the land records data set, and then provide the solutions or provide the framework for the banks, like State Bank of India or other banks, to provide or facilitate the agri-input related loan and the finance. So once the finance and all these evidence-based mechanisms that will come in play, the challenges will be reduced. So I did not answer specifically your question of what are the challenges that smallholder farmer face, but these are mainly the challenges that are practically on the ground that we have seen for smallholder farmers, where land sizes are small, the data sets are not available, and the issues is that they find funding mechanisms, they don't get evidence that what is the particular crop that has been cultivated and what was the yield that was produced. And that evidence actually is needed to get better funding and to increase the productivity and get better finance or get the access to the finance. And the other part is the second question, I think, is how multimodality data set used in smart agriculture with federated learning. So these are huge words, federated learning and the smart agriculture. So as I said, regenerative agriculture, as I was saying, small things are there, like you have to monitor the cover crop, you have to monitor the tillage, then you have to monitor some other aspects. So these are like actually multimodal data sets that are coming in play. For example, for tillage identification, you may be using synthetic aperture radar like Sentinel-2, Sentinel-1. But for cover cropping, you may be using time series of Sentinel-2 data, which is optical. So like that, these multiple model data sets are coming in play. So there was another question which I skipped last time in the last question sessions, is actually about how satellite, drone, and IoT sensor data can be integrated into unified geospatial platform. So real-time monitoring right now, multiple startups are there. There is a Cropin and other companies are there who are actually providing such solutions. I think they, and also we also use it. See, IoT is a very good word to as such use it, but there are certain limitations. We cannot place sensors at every place, but the weather data sets from different sensors can be integrated. So right now we are doing that. So wherever there is a weather forecast data set is available, and then there is a IoT sensor, which is weather sensor deployed on the field. We fuse this data set and understand irrigation water requirements. So one of the use case was there, where we have already used that kind of mechanisms in the absence of IoT sensor and with the presence of IoT sensor. So this mechanism of irrigation water management, it takes care of both the things. The weather related parameters coming up from the weather forecast or weather systems, and also from the IoT sensor. And then the irrigation related requirement is, or water requirement is calculated based on both the inputs. That way the fusion is being done. And this is also done by multiple other companies for the information generation for irrigation related scheduling. Any other questions? I hope the session was informative enough to all of you, and wish you all the best. Thank you for giving me this opportunity.
So there was
please go ahead.
one question from the participant. What challenges do farmers face while transitioning to regenerative farming?
Yeah, see, regenerative farming, until and unless there is actually the incentive that is provided by government is not looked up into, it's very difficult to do that. So in regenerative farming, transition can be from very small activities like reduced usage of pesticides, fertilizer, that is chemical fertilizer, and then the use of practices like, for example, cover cropping, green manuring. So there are list of practices that are there for the regenerative agriculture practices. Like when there is a livestock farming, like there are cattle or the goats are there, then instead of going for the closed cultivation, like for example, harvesting the crop very frequently for the goat or livestock, they can also maintain a proper regenerative process of shifting the goat farm from one location to other location and having it an open kind of a goat cultivation or the livestock cultivation. So that kind of things are actually coming in play in certain areas, large geographies. But in India specific conditions, we can follow certain practices where the output going from our farm, that is actually in terms of agrochemicals or pesticides or harmful chemicals, that needs to be reduced. So that is, I think, the part that we need to focus.
Thank you, sir. Sir, there's one more question. How does regenerative agriculture influence long-term water conservation?
See, the long-term water conservation can be facilitated by certain practices like cover cropping. So if there is a cover crop available, the erosion will not be there, and whatever rainfall that is there, the cover crop will uh, put that rainfall within the particular field itself. If there is excess rainfall, it will definitely flow away from the field. But if there is no cover crop, then the soil erosion and the water will flow out of the field, and that will cause the soil loss and also the water scarcity during the period when there is no water available. So it depends upon region to region again. In certain areas, it is absolutely not possible to conserve any water. Like mountainous terrains, there is a high hilly slope is there, and the terrain itself is not facilitating that kind of a water conservation. So there are certain other measures that can be taken in terms of the construction of community ponds or community farm ponds like that. And those aspects are actually already being incentivized by the government, and their monitoring, etc., is happening using the geospatial technologies. So these things are coming up in India also, but in European geography and other geographies, they are very extensively being monitored using remote sensing or geospatial data sets.
Thank you, sir. Sir, there's one more question. Sir, my UG students are working on forest degradation monitoring work. I want to know what are the best practices to distinguish seasonal fluctuation from actual degradation when working with crop cycles health monitoring.
Yeah. So here in this question, actually, you're asking about two things. One is about forest and another one is about crop. So if you are talking about agroforestry systems where your crop is within the forest kind of a system, like a coffee plantation or something, then I think this forest degradation is actually, you can look into the time series, long-term time series from the historical time periods. So if you take Sentinel-2 into consideration, from 2017 data will be available. If you take Landsat into consideration, the data will be available almost from 1990s. So you can understand how the variations or the forest canopy conditions were there, and then based on the forest canopy conditions, how the agriculture intensity is impacting these forest systems. Like for example, there is a agriculture which is very close to forest, not the agroforestry system. Then this agriculture is going to have impact on this forest because this agriculture is expanding and it is going to encroach into the forest system by removing 2 or 3 trees, or by removing certain trees after some point in time. So clearing up the forest. So I think that activity you can monitor using the time series of satellite data. So you monitor the intensity of agriculture, and then you monitor the change in the forest that has happened over the time. And I just want to remind you that forest also has its own variation across the year. Like some forests, like deciduous forest, they show the seasonal variation. So you have to account for the seasonal variation. It is not actually the degradation that is happening. It is a seasonal variation within the forest that is happening. But the degradation is actually the cumulative effect of the change that is impacted by the agriculture pressure or anthropogenic activity. So I think some ground truthing is also required in that kind of thing, where you have to visit and select some photographs for the current condition and then look for the historical condition. What was the condition in the past in that area? So definitely the time series of satellite data will help you in this part.
Yes, thank you, sir. Thank you.
So we have one more question from a participant. How can geospatial platforms ensure data accuracy and reliability in heterogeneous landscapes?
See, in the heterogeneous landscapes, if there are pixels itself, they are not pure pixels. Like for example, within a 10-meter pixel resolution, if there is a heterogeneity, then there are certain mechanisms like superpixeling or using the high resolution, very high resolution satellite data. And in geospatial data sets, the drone data or the aerial photography is also considered as a geospatial data set, not only the satellite data. So whichever data set which has a geospatial latitude, longitude embedded into it, or the special information embedded into it, they are called as a geospatial data set. So drone data sets can also be used, and see the accuracy and reliability is actually in terms of reproducibility of particular claim. So in European geography, I will give one example, or in also India geography, there is a certain example of evidence. So when a farmer says, I am taking a loan or insurance for a cotton crop, now the farmer has just said that I am taking a loan for cotton crop. But in actual in the field, if the farmer has cultivated some other crop, not cotton, how do you do that? How do you assess that? So for that, what you will do is like you will understand the satellite data and interpret it for the cotton crop and understand whether the similar pattern of cotton, the cotton is a 5-month crop, whether the vegetation variation is happening for the 5 months or it is changing within the 3 months. That is a simple example I am telling you as a part of solution. So this accuracy and reliability is actually coming from that aspect. The second part is the cloud cover and other aspects, which are like pre-processing steps in the satellite data. So that are also need to be taken care of, where the data gaps are actually going to be very important. So if there are a large number of data gaps, then your reliability will be less in interpreting the results, and also reproducing the output. So these are some aspects that we need to be into. I hope I try to answer, but may not be a clear answer, maybe.
Yes, sir. So participants, is there any questions? You can unmute and you can ask the question or post it in the chat.
Yeah, I just want to check, was my voice audible clearly, or was there any like fluctuation in between or any noise in between?
It was all clear, sir. Whatever you said, it reached us very clearly.
Okay, okay. And I think the presentation will be shared, right? So I'll be sharing this presentation in PDF format. You can and share that to the participants.
Okay, okay, sir. Okay. So I think there's no more questions. Okay, so we have come to the end of this session. Thank you, sir, on behalf of the entire APSIT and the entire organizing committee and all the participants. We express our sincere gratitude to Dr. Suryakant Sawant, sir, for an outstanding and informative session and taking us into the platform of the role of geospatial technologies, in agriculture. So you have taken us into a different domain and made us understand even the complex things in a very simple way, sir. Thank you so much for your deep technical insight. The practical examples, engaging delivery has provided us with a rich learning experience. Thank you for your valuable contribution and for inspiring us with your work in this crucial field, sir. Thank you so much.
Thank you.
Thank you, sir. I mean, from the session, I must say, many of us will find the research topics and new ideas to be given to our students to work on. It was really helpful. I mean, to this depth, we were not aware about it. So, thank you, sir. Thanks a lot.
Yeah, I tried to consider that all of the participants are not from same background, so I started from the basic. Yeah.
Thank you, sir. Thanks a lot.
Thank you. Thank you.
Dear participants, the link for this particular session, the feedback and the attendance link has been posted. So requesting you all to fill the link now, okay, for this particular session. And we will be starting the session in the next 5 minutes. Okay, we'll take a break and then we will continue with our next session. Please stay connected.
Hello, ma'am.
Hello, ma'am. Hello, everyone. Yeah. Can you hear me?
Yes, ma'am.
Yes, yes.
Okay. Good. Thank you.
Ma'am, can we wait for 3 minutes and then we'll start with the
Yeah,
session at
sure.
5? Is that okay?
Yeah, sure. No worries. Thanks.
Okay, welcome everyone for the third session of the day. So, yeah, so it's my privilege to introduce the esteemed speaker for today's session, Dr. Ujjwala Chaudhary. She has obtained a doctorate degree from IIT Bombay in massive data analytics using high performance computer in 2017. She has worked as associate professor in KJ Somaya College of Engineering. Now she is a research fellow high performance computing at London South Bank University, UK, in Bioscience and Bioengineering Research Center at LSBU. She is a researcher with comprehensive expertise in analytics, machine learning, deep learning techniques, and high performance computing platforms, proficiency to work on research challenges that require extensive data exploration and big data analytics by accelerating the process to solve real world problems in different domains. Her research interests are biomedical imaging analysis, knowledge discovery from Earth observation data, business data, high performing computing, geographical information system, machine learning, deep learning, data exploration and big data analytics, and database technologies. It gives me a great pleasure to extend a warm welcome to our esteemed speaker who will be delivering today's session on the highly advanced and impactful topic, optimizing AI algorithms for geospatial analytics on modern HPC architecture. This session brings together two powerful domains. One is artificial intelligence and high performance computing. We eagerly look forward to gaining valuable insights into optimization techniques and HPC frameworks that are shaping the future geospatial intelligence. With a great respect and enthusiasm, I now invite our distinguished speaker to deliver the session. Thank you, ma'am.
Yeah. Thank you, ma'am. Thanks a lot for this kind introduction, and we're happy to share my experiences along with all the participants. And yeah, thanks again for giving me this opportunity. Okay, so I'm sharing my presentation. Please let me know whether you can see it. Yeah, can you see it now? Hello, can you see the presentation?
Yes, ma'am.
Yeah,
It is visible.
thank you. Thank you. Okay. Okay. So as Madam has, she has mentioned, so I would be focusing more on the HPC technologies which we can use. What are the optimizing methods? I mean, how efficiently you can optimize your algorithms or whatever the methodology we are using while analyzing the geospatial data. So main focus is on these techniques. Okay, so yeah, first of all, I'd like to explain that why there is a need of high performance computing technologies in this spatial data. Typically, I would say the remote sensing data. Okay, so this talk is more towards the imaging analysis of the spatial domain. Okay, so the first characteristics of this spatial data is variety of data you can collect from the remote sensing. So some of the data may be collected from the spaceborne, like the Earth observation satellites. Then you may collect the data or you may get the data from the airborne. It may be the local data captured using the drone. Then again, the variety of the spectral variations, like considering the multispectral data, hyperspectral data. Okay, so basically, we may embed multiple data sources to come up with more robust, can say, model. So yeah, so variety of data we consider. Then secondly, volume of this remote sensing data. So if you'll see, I mean, the volume is really, the hyperspectral image, if you consider there are almost 300 bands, 300 bands, the images captured with different spectras. Okay, again, if you consider the very high spatial resolution satellites like QuickBird, where where each of the pixels would be represented in terms of centimeters, so you just can imagine the kind of data you have to process. And again, we never perform the analysis on a single image or the data collected at one time stamp. So we usually cover a temporal data, the data captured at different times stamps. So yeah, so obviously, for change detection and any of the analysis, where you need to compare the data from the past and want to predict the future, obviously you'd be using the temporal data. Okay, so huge amount of, huge volume of data is there, you can say, for this remote sensing. Again, nowadays, the advanced or the innovation in electronics field, where you increase, where the data transfer rate has been increased, or your downlink capacity, downloading the data from the satellite, that capacity has been increased. The speed up is observed, good amount of speed up. So that's another, you could talk in terms of velocity of this remote sensing data, which is also very high. And on top of that, we try to apply a variety of methodologies with thumb rule saying more the complex algorithm, better the accuracy. Okay, so the complex algorithm, again, it's a very time intensive algorithms. We know that deep learning algorithms nowadays, the advancements in AI, if you consider the current advances like the generative adversarial network GAN. So it's training on the GAN model, it's too intensive, okay, computationally intensive task. But then, yeah, we have to use it because then it improves our accuracy. It helps us to generate the synthetic data, which because sometimes we won't be able to, sometimes we need to pre-process this huge amount of data. So, always we need to pre-process, but then, yeah, so we may use this kind of computationally expensive algorithms just for the sake of pre-processing, not forget about the actual analysis. But then even for the pre-processing, we are using such a heavy algorithms like data augmentation. Okay, so overall, the as compared to the earlier time, nowadays we are using really very computationally expensive algorithms to improve on the accuracy. So that is one of the main thing. And then again, being as a researcher like us, we want to see the result quick, so that we can update the model, can run it. So uh, that is also our, I mean, from the end, or even if you consider the end user perspective, which requires a decision making in the real time or near real time, then uh, yeah, of course, with a remote sensing data which has these big data properties, it's quite difficult to process it faster or in near real time. So what solution we have with us is this. Again, yeah, one more thing, just addition to this earlier point, what are the challenges? Now again, the geospatial domain is nowadays becoming quite demanding. Okay, so because I mean, it's like if you consider the granularity of a data, okay, now people are understanding, the businesses or the government is understanding the importance, or you can say the realization of the granularity of a data or analysis. For example, country, I mean, the analysis which you will do at the country level, uh, at the state level, and at city level. Okay, so uh, more the deeper you go, larger the data involved in the analysis. For example, for entire country, you want to do the state and city-wise analysis. Of course, so huge amount of data is required in this case. Again, for capturing the entire country, probably you may be using different satellite, maybe the Earth observation satellite you will require, where you will get a, uh, per pixel resolution maybe in terms of 10 meter or 1 kilometer. But then at state level, even if some of the uh, I mean the satellites which are having the little higher resolution would be useful. Okay, similarly at the city level, you may use airborne satellite images, okay, just like captured by the flight and so on. So where you will have very high resolution, like in terms of millimeters and centimeters. Okay, so now you think of a problem statement where you have to analyze, say, the water resources across the country. Okay, so water resources across the country, probably um, you could be able to capture the high level view using the earthborne satellite images. Then maybe you would be using some airborne, again, some high resolution satellite images for the state level analysis. Okay, but then when you'll go to the city level, okay, I mean, each city, how much of water resources, the natural and all that, I mean, that kind of bifurcation, the natural resources and the man-made resources, the utilization, whatever, the dam, I mean, all related information regarding the water bodies. So that kind of analysis, when you'll do at the city level, state level, country level, probably you'll end up using data from variety of sensors. You are integrating, you are doing a lot of pre-processing so that you should not miss the on the overlay. Okay, because I mean, of course, at whenever you aggregate the thing at country level, when you overlay your city and state level layers on that, there should not be mismatch in terms of the boundary or the contours. Okay, so yeah, here the point I want to say is lot of pre-processing and data, and you can say the operations you need to just perform to ensure the consistency, the accuracy, the sufficiency of your data, basically quality parameters of the data. So as you will improve these parameters, obviously you will get a good or excellent insights. Okay, so these are the prerequisite, and because of this, I mean, the businesses are now realizing, or the government is realizing the importance of this different levels of granularity, what kind of information it provides, how it would be useful. So obviously, but then for a developer, it's a huge task to combine the data at different scales, different resolutions. Okay, we need to integrate that data. Integrating is not that easy. A lot of pre-processing we need to do. Okay, each level there will be a separate analysis and then integration again. So just think of the kind of volume the processing is involved into that. Okay, and again, kind of questions been raised or needs to be answered to the end users, like what has happened in the past, what could happen in future, what are the provide some solutions or on the possible outcomes if something is not it's not whatever the results been or the outcome is predicted, how you can just uh, improve on that. So that's basically the prospective analysis. So descriptive, predictive, and prescriptive analysis, these are what are being expected to be answered or provided based on this geospatial data. Okay, so these are the few reasons why we need to involve the HPC technology, the high performance computing technology in this spatial domain. Okay, spatial data exploration. So we'll look at the different high performance computing technologies available. But then before we jump to that, just understand the basics of parallel computation, which the computer people, computer IT people, they already have some background about this parallel computation. First is a partitioning. We always need, when we perform the computation in parallel, we need to always ensure that whatever the task we are performing in parallel, those tasks are independent of each other. So, partitioning can be done at the task level and data level. So probably we end up dividing our computation or we end up dividing our data into multiple places. But then doing that, we need to ensure that there is no dependency as such in terms of computation or in terms of on data as well. Okay, so considering that we do the partitioning, then when we partition the data, so obviously partitioning is parallel computing is possible only when you have multiple cores or the processors are available to process in parallel. Okay, so you are dividing your data and giving it to the multiple processors. So of course, there is some local communication and global communication involved. So here, whatever the communication I am mentioning, it regardless of any of the HPC platform, which can be used for high performance computation. So it involve even you use the GPU or you use a cluster, whatever the cloud. There is a local and global communication. There is a synchronization happening at multiple levels when multiple processors comes into picture. Okay, so that is the communication. Okay, so after the communication is also very important aspect in parallel computing, and since it has a cost involved into that, we should always try to optimize the communication, optimize the or rather optimization, I would say reduce, because optimization always in terms of reduction of the communication in terms of this communication, maybe the data transfer or the method transfer, method in the sense the procedure which you want to run or the task, the algorithm you want to execute. So whatever you would like to communicate, it should be minimal to improve on the performance. Then comes the agglomeration. So it's agglomeration is grouping the tasks into the larger tasks. So basically, this is something. We just aggregate the results just to come up with. So with the final one, that's how you could say the agglomeration. We just group the things, group our results, maybe the task here, maybe the data. Okay, so agglomeration again at different levels. Mapping. So yeah, assigning the tasks to the processor. So mapping plays a very important role because it ensures the balanced distribution of work. As I said, that parallel computation is only possible when you have multiple computers or multiple systems at place, okay, or multiple cores are there to process, then only we can do the parallel computing. So when we do the parallel computing, we need to always ensure that we would be distributing the data across, or maybe the instructions or the task across all the processor, with, so that each processor get equal load, basically balanced load. So mapping is very important aspect when it comes to the balancing of the load. Okay. So yeah, so parallelization, as I said, that we need to divide or the partition our data, not only data, we can even partition the task. Okay, so we refer it as typically the data parallelism when we divide the data across multiple cores or multiple CPUs or nodes. And then there is a task parallelism when we divide different operation across multiple nodes or multiple cores. Okay. So in terms of, when we discuss the granularity in terms of parallel computing, it is basically the qualitative measure of the ratio of computation to communication. As I said, computation is very important. It's actual processing, and communication is something which is, the communication is something kind of a transfer of data or control messages, where which will help you to complete your computation. Okay, so it may be your instructions, which commands you want to run, or it can be your data. Okay, it's a the granularity we say in terms of the ratio of computation to communication. Okay, so accordingly, we have for this, considering the granularity of this computation to communication, again, we can do the parallelism at two different levels. One is a fine-grained parallelism, okay, and another one is a coarse-grained parallelism. So we'll just describe those as well. But then here the important aspect to consider is that the time period of computations are typically separated from time period of the communication. Okay, so computation we consider, we typically, it's for, if you consider holistic view, yes, of course, we start by counting the time or measuring the time starting from submitting job till it get executed. Okay, but then, yeah, of course, just to analyze that how much of time get utilized for the communication, the synchronization as compared to the computation. I will be showing the plots where you'll realize that how much of the difference is there when we say the computation and communication cost, and how it affects your analysis overall execution time. See, this is something we are looking at because the several reasons which I had given, that we have the high volume of it. Basically the big data we want to handle, and we want to process it fast just to support some kind of near real time analysis, or for researchers to give faster feedback. Okay, so yeah, so looking at all this, what I will summarize in terms of parallel computing, that many computations are carried out simultaneously. Okay, different computations we perform in parallel. Then for that reason, we may break our data or task into several subtasks. Okay, then each of the subtasks is get performed by the worker or the process. Basically here the worker and process is nothing but we are utilizing a separate processor to execute that task. Okay, so then the processes, these different cores or processes may need to interact with each other in order to solve that particular problem. Okay, and then they may communicate with each other, share the data with each other. Okay, so yeah, so this is just I have summarized the way we do the parallel computing. Okay, still I have to cover the different technologies, but then I'm just giving the background so that when I'll jump to the technologies and I will try to explain that in each of this technology, how the data is get handled. So, or the parallel processing is done. So, I mean, you should have some background to that. That's why I'm covering this aspect. So now, since hopefully, I mean, you had a good idea about what we do in the parallel computation, and we also seen that there is a fine grain parallelism and the coarser grain parallelism. And then this granularity depends on your computation to communication ratio. Okay, the granularity we say in this parallel computing as a computation to communication ratio. Okay, so fine granularity, obviously it's there is the very low computation to communication ratio. Okay, this is not something we expect, but yes, there are some HPC technologies which really works very well, even if you have the low computation to communication ratio. And the best example is your GPU, okay, graphical processing unit, because it has been designed for this fine grain parallelism only. Okay, so fine grain, just to understand it easily, whatever the pixel level computation we perform on the image, all those can be referred as a fine grain parallelism. Okay, so and that to be on the HPC system like the GPU. Okay, so because GPU is the only one which allows you, I mean, as of now, in whatever the platforms I've worked on, I observed that GPU is the only where you would work at the pixel level parallelism. Okay, it enables you the pixel level parallelism. Okay, but still it performs much better, though having very low computation to communication ratio, which we actually, I mean, parallel processing, we always expect that this computation to communication ratio should be high. There should be more computation and less communication. But I mean, here, since GPU is with the help of the multiple cores, the CUDA cores, it has the kind of capacity it provides. I mean, I would be discussing the architecture also in the brief, so that time I'll explain like how it would be useful. But yeah, so discussing about the fine grained parallelism, uh, we perform a very small computation, okay, but there is a good amount of communication involved into that. But since we are distributing the data, okay, at pixel level, so typically if you consider the GPU case, one core, one CUDA core, one pixel, or one thread, one pixel, that kind of thing. So it it supports excellent load balancing. Okay, because pixel level distribution we are doing. So every core would be having, or rather core, I should use the word thread. So every thread will be handling one pixel. So yeah, I mean, excellent load balancing happens there. And then it implies, but then moving the data, so high communication overhead. And overall, if you see the overall performance, the speed up is get hampered by the communication cost. Okay, so overall computation performance or overall speed up get hampered by this communication cost. Okay, so and then sometimes it also happens like if the granularity is too fine, okay, it is possible that you may require, I mean, spending a very high time, I mean, large amount of time on communication and synchronization as compared to the computation. And then you may observe that, yeah, your performance is actually dropping, even if you compare it with the uh, sequential CPU execution. Okay, so yeah, that's one issue we may observe. And yeah, I mean, it's basically if you have really a massive data, computation is too complex, uh, you can see a good amount of speed up over there, good performance you could observe for the fine grain parallelism. Okay, but then coarse grain parallelism. Okay, so what we do here, that coarse grain is like your computation to communication ratio is high. That means you have higher computation as compared to communication, Okay, means you are using a large computation across multiple worker or multiple processor. Okay, so relatively large amount of computations are being done at each of the node. I am saying it node, and for this coarse grain and then fine grain, I am saying threads, because that's how the HPC is. I mean, because the platform changes the moment you say the fine grain and the coarse grain, because as I mean explained, that the GPU is where you can do the pixel level computation. Okay, so it's a fine grain. So even if there is a low computation to communication ratio, it is still outperforms your CPU. Okay, I mean the sequential processing, not CPU. It outperforms your sequential processing. So fine grain parallelism, you can just make a approximate, I mean, equivalence to using the devices like GPUs whenever you try to get a fine grain parallelism. But whenever you think of the coarse grain parallelism, always the cluster computing or the cloud computing technologies would come into picture, because then this has been done with a multiple nodes. Okay, um, and because there large computation we can ask to each of the node to perform, and then yeah, I mean the analysis would be at the course level. So the MPIs, the uh, cluster parallel processing, you can say the platform, that is a message passing interface, MPI, we can use. MPI is one of the high performance computing platform that can be used for this coarse grain parallelism. Okay, where you see again a good speed up, but yeah, I mean of course there would be a communication cost involved into that, but then yeah, there is more opportunity for performance increase, harder to load balance efficiently, which is there. I mean, load balancing can be done very easily with this pixel level computation, but whenever it comes to the coarse grain parallelism, it becomes difficult to balance load equally across multiple nodes. Okay. Okay. Yeah, and then you can scale up with the help of memory scaling, typically provided in the cloud computing. You can scale the resources as per your requirement, the storage as well, like storage, and because now storing this huge amount of data is another challenge. So yeah, and then transfer cost for this is also high. For this fine grained is also quite high. So yeah, so this is one of the, you can say, one of the enablers you can use, that storage, and then faster access, like similar to that of direct memory access methods. You can enable, you pay extra and then you'll get a high speed for transfer. Okay, so yeah, so the technologies which I was discussing is like cluster computing. Okay, so cluster computing, where we integrate multiple nodes. Essentially, each node must be configured with the same whatever this is, same parameters, like all your configuration parameters. Everything should be same. Your operating system, everything should be same. So that's how the device hardware, everything should be typically been from the same of the same configuration. That's how the clusters are made up of. And then the distributed computing or the heterogeneous, you can just compare it with your cloud computing, where systems of varying architecture may be part of your thing, because then there is a kind of wrapper which ensures that seamlessly the devices will contribute in parallel process. I mean, contribute in the processing. Okay, regardless of the underlying hardware and the other aspect. I haven't worked on the cloud as such by using the heterogeneous platform, but yeah, I worked on the clusters and then the GPUs. Yeah, and then there is one more device, which is specialized device, specialized hardware, just like a general purpose GPU, graphical processing unit. Uh, the device is FPGA, the field programmable gate array. The people from the electronics background, they might have worked on this FPGA kit. Okay, but then the card comes which you can insert on your motherboard, and then yeah, I mean, it needs to be configured. But then yes, that is also one of the device being used uh, to explore the parallel opportunities, parallel processing opportunities for such a, I mean, complex data processing. Okay. Again, the edge computing technology is typically used whenever we need to process the data closer to the source of the data. For example, at some of the sensors, say temperature sensor, we want to we want to say calculate the average temperature of the day. Somewhere on some day, if the average temperature goes exceeds certain limit, then the alert should pass through. So this kind of small things, when it needs to be processed but then involve a good amount of data, then you can use uh, the again NVIDIA Jetson, again parallel computing technology, but then a kind of chip or card which you can use at edge, which will process your data speedily. Okay, but then with a limited capacity, we know that the edge computing technology, since those are used at the source where the data is being generated. So whenever such a data is generated and need to be processed in real time, the example which I had given, so to give alert whenever the temperature goes beyond certain threshold, or some of the parameters, say typically for precision farming and all that, this can be used. So maybe just to alert the end user that something needs to be acted on, then in that case, this edge computing technologies can be used. So just like, see, the GPU, whatever the GPUs I'm referring, we all know that those are the NVIDIA GPUs. So NVIDIA also has the Jetson board, which are little low capacity as compared to the GPU cards, but then of course has all the capabilities like CUDA enabled small capacity GPUs, which enables you process the task in parallel. Then we know that the Raspberry Pis are also there. Then there is a Google Coral, which is also providing the parallel computing processing capabilities at source, basically. Okay. Yeah, so these are also HPC, things which you can use at edge. Okay, and then since my focus would be more on the GPU, just like, this is my favorite diagram. Because it's quite simple, but then yeah, it's very easy to understand the architecture and then how it is suitable for our images. Not only the images from the geospatial domain, because currently I'm working on the biomedical imaging, and then there also I use the GPUs. So basically, the GPUs are really very, you can say, the handy HPC technology, which really give a very high speed up as compared to the other platforms which I have used. So yeah, so this architecture I'll explain. Like in the GPU, there are multiple multiprocessors, and each multiprocessor has a multiple processors. And since we say that the architecture of GPU is a single instruction, multiple data. Okay, so there is a single instruction unit over here, and it gives same instruction to all the processors. Okay, so same instruction has been given to all the processors at one shot, and what each processor will do, each processor will execute that instruction on its data. Okay, so you may say local memory, in each processor has its own local memory, and there the data of that whatever is to be operated on. Okay, so holds basically, the related data which is there on the in the local memory. Okay, but then basically it's a thread which is pointing to this memory location. Okay, so here we are dividing a data across multiple processors or multiple threads. So data is there to each of the processor. Only whenever the instruction is given, then the same instruction get executed on all these data elements in parallel across all the multiprocessors. So you just think of, I mean, what level of parallelism has been achieved. Something, if the processors need to communicate with each other, then there is a shared memory. You can see the shared memory where the processors can communicate with each other using this memory. If the multiprocessors wants to communicate to each other, then there is, yeah, of course, there is a global memory. So global memory, some of the variables you can store there, which has been retrieved by the multiple processors. Okay, so these are basically the typical architecture of the GPUs. Okay, where we have the multiple processors, which are nothing but, I would refer it as a thread, which points to each of the data element. Okay, so GPU is really suitable for remote sensing images. Like the architecture is a single instruction, multiple data. Okay, so image processing also, I mean, we will say that the GPU architecture is very much complementary to the image processing algorithms. Uh, I mean, why this statement is quite meaningful, that the image processing algorithms are complementary. I mean, the architecture is complementary to image processing algorithm, because we know that the task which we do on one pixel, we end up executing the same task or the operation on all the pixels, right? I mean, maybe it will be involve some kind of neighboring operations, like say we apply say filter of 3 by 3. Okay, but then whatever we do on one pixel, the same operation we do on all the pixel in the entire image. So basically we perform a single operation on different data elements, right? So your single instructions would be there in the instruction unit, and then you will have all the data at your different processors, right? So that's how the GPU is too suitable. The architecture of GPU is too suitable for image processing tasks. What do we do in the image processing? I tell, we apply the filters, we apply different kind of kernels, Gaussian, all that. I mean, whatever, basically the neighboring operations we do a lot while processing the image. Okay, so even now our deep learning algorithm, based on, since it's an image, those are the convolution operations, right? So it's a convolution neural network. But then what do? We just keep on applying different filters, try to extract different features. But just think of like multiple operations we are performing on the same data. So of course the GPU architecture is very much suitable for this kind of uh, operations, image processing operation. Okay, so same operation is basically performed on each pixel, hence suitable for the task parallelism as well. Okay, we know that the image is basically the representation. It's just a matrix, right? So matrix, rows and columns, and the thing is, in the GPU we can even view the multiple CUDA cores in terms of a matrix, rows and column. Okay, just as out of the matrix we have the x and y uh, variables. Similarly, those x and y we manipulate while handling the data on the GPU as well. Okay, this is something where I'm telling, when you will actually work on the GPU with the CUDA coding. But nowadays, yeah, I appreciate a lot of development readily, the packages which are available like PyTorch, TensorFlow, all these I mean, it's so easy to apply or to use the GPU during your analysis. While you do analysis, it just detect the device. If it's a GPU, then yes, run it on the GPU. So basically, because of this ability of these standard libraries like PyTorch and then where are Keras, which enables you to get the GPU access with different APIs or wrappers around it. So the developer doesn't understand what actually goes at the back end. Okay, but then yeah, it's important to understand that how much of speed we get and why do we get it. Okay, so this is just I'm trying to give the realization so that when you will use, even I don't expect that everyone should do the CUDA coding and then do the parallelism. No need to do that, because now readily the packages are available, so one should use those packages and work on that, unless and until the work itself is on parallelizing the algorithms. The contribution is in terms of the parallelization of the algorithms. So if not that the if not that is objective, then of course you should use the PyTorch and all that. But then while using that also, you need to understand that what parameters you can set which will optimize your execution. Yeah, so here I'm just trying to show you that what different things you can use. For example, CUDA, when you have the multiple GPUs on your MPI platform, then yeah, you can use the MPI run. Okay, but then you have the Horode, where I mean similar commands just like you give in the MPI. Though, so you can give the Horode run hyphen number of processors 8. Okay, so host would be, you need to provide a host name. Then you probably from that particular host you would be using 4 GPU. From another host you would be using 4 GPUs. Then run your Python code and then train this particular Python. I mean, basically train.py. This is what you do your training typically on this cluster company, or MPI run. You can straightway say MPI run hyphen and as many processors, CPUs you would like to use /train. Okay, then PyTorch, we always know that uh, there is a distributed, when PyTorch distributed is also there, which will help you to run it on the MPI. So MPI, we refer it as a distributed data parallelism. That the GPU parallelism is not actually the distributed one. Okay, whenever the multiple nodes will come into picture, that becomes a distributed. So TensorFlow also, if you want to use the MPI kind of like where you have multiple nodes connected, so basically the cluster thing. So I'm just giving it here because I mean a lot of details and examples are available at each of these library. Also, the data transfer optimization needs to be considered, because as I said, that even if I mean it provides you the fine-grained parallelism because pixel level work you do, but when you move the data, you need to always ensure that, because while loading the data, this statement might be very much familiar. Everybody must be familiar to this statement, right? This is one of the statement from the Python PyTorch, right? So we create our train loader. Okay, the data ready to load. Okay, so data loader, we say give our training data set, then batch size, whether you want to shuffle or not. So always say, I mean, of course, if you have that GPU there, of course, you should say the pin underscore memory equal to true. Okay, so you are instructing the GPU device, not only GPU host, because host in the sense your CPU is responsible for allotting the pinned memory, and then the GPU must use that pinned memory. So what is basically the pinned memory? It's a memory, it's a region from your CPU which has been reserved explicitly for data transfer with GPU. Okay, same set of memory locations, same set of addresses, the GPU will always read. So that's a pinned memory. Okay, so whenever you explicitly allocate the memory on the CPU, the transfer become faster. Okay, so always use the pinned memory transfer when you use a GPU basically. So this is true only when your device is GPU. Okay, this statement. And then while loading, you can use the number of workers. Now here, the number of workers are actually the CPU cores. So how many cores you would like to use? So these are not the CUDA cores. Okay, those are the CPU cores which will help you to move the data in parallel. So that's how is a I mean, if you have quad core, you can say, I mean, so one core you can just keep for other tasks, and then rest half. Like if my system is having total 12 cores, then 10 cores I can always use as a number of workers. I mean, obviously, I mean, it's not always like if you have that kind of huge amount of a data, then only it makes sense. Otherwise, you will not see any performance improvement. Uh, you would only see the performance improvement if you have a huge amount of data to load. Otherwise, if you increase the number of workers and there is no sufficient data, in fact, you are increasing that. I mean, you are just wasting the time, because allotting and then moving to each of the processor and then aggregating, it is very time consuming. Okay, so unnecessary, you are splitting the data across multiple workers. That is also not good. It will hamper the performance. Okay, so yeah, and whenever possible, use the shared memory, because shared memory is something which is accessible to all the threads belonging to some multiprocessor, and it has a faster transfer as compared to the global memory. Okay, but then what you can do, I mean, this is something which you can always do. I mean, the piece of code you can write in the C CUDA or some of the platforms, say Java CUDA, any of whatever and then you can always call that module in your Python code. Okay, you can check for the syntax. So that's not, I mean, some of the thing, if you really feel that it's taking a lot of time, so but of course you have to have the CUDA programming skills for that, even to write that small you can say the code snippet to allow the data to put on the shared memory and then retrieve it from there. Okay, so batch data transfer, so that batch data transfer should be again fewer but larger transfer. Okay, then yes, there is asynchronous transfer possible, where you can start transmitting the data, and then whatever the data has been transferred in the stream, you can start the computation simultaneously. Something which is not hampering the overall, or something which is not depending on the entire data set. So because the pixel wise, if we do the computation, then whatever data been the batch has been transferred, the computation can be set. So that's asynchronous transfer. Even you can transfer multiple data asynchronously, and computations can be performed asynchronously. Okay, so this is for the GPU transfer. And then what if you use the MPI transfer? So MPI, as I said, it is a message passing interface. This is the I can say that programming platform on cluster. Okay, MPI, Open MPI, basically it's Open MPI. It's a programming platform on the cluster. So in this typical configuration, if you have to send the data to all the processors across the entire cluster, okay, same data, if you need to send to all the processor, then you can use the MPI underscore broadcast, bcast. MPI underscore bcast it stands for broadcast. You broadcast the data to all the nodes. Okay, so if you think about using MPI on your PyTorch and all that, you would be getting similar kind of statement. Only the syntax would be there. So in place of MPI underscore broadcast, there would be something, some other you can say keywords where you can broadcast the data on MPI platform. Okay, then MPI underscore all reduce when you have to collect the data from all the processors. So it really improves your transmission very I mean efficient. it makes efficient transmission when you use something like MPI broadcast or MPI all reduce. Then there is a, when you have to send something to the root node or from its from the computing node to the root node, you may aggregate the results or whatever the messages you want to send. Say what messages, whatever the results or data, it is basically a message moving from one node to another node. So always try to aggregate the messages. So I mean, so that you should have the large chunk of data. As we have seen, that large chunk, sending large chunk of data is more efficient than sending a very small chunk of data. Okay, so that's what you need to take care of. Yeah, and of course, try to balance the workload along the multiple processors, because MPI, as I said, node level. So GPU, we can balance the data very well. Okay, but then MPI, there is no, usually we use for the coarse grain parallelism. So we don't get much, you can say, much kind of flexibility to balance the workload. Yeah, but we should always try to. I will show you the example how I have tried balancing the workload even on the MPI platform. Okay, then always profile whenever you use the HPC platform for analyzing. So we should always use the profiler. Okay, so profiler that helps to identify how much has been time spent on the communication and where you can optimize it, how much of the time has been spent on actual execution. Okay, so and then accordingly you can just, I mean, if there is a further feasibility of optimizing, you can always. Okay, so this is something, a PyTorch profiler you can see. Okay, so suppose operation is a matrix multiplication. So how much is a CPU time taken in the millisecond? Then CUDA time, how many times it has been called? Okay, how much is memory allocated on that? Okay, so ReLU operation happening on the CPU, not on the GPU. How many times? 10 times it has been called. So CUDA convolution, of course, convolution whenever it comes, like all the operations, like whenever you move your kernel or same operation get performed on all the pixels, it is a CUDA candidate. Okay, so 60 milliseconds, nothing has been done on CPU, only on the GPU. Okay, 5 times it calls. Okay, it occupies. So you try to see that what is been done. I mean, even if you see set ReLU to run on GPU, you would see here in place of 15, you may see 30, 35 more time being consumed by the CUDA. There are certain sequential operations involved into that. So it can't be the candidate to be run on CUDA, right? Okay, so just a visual profiler. Okay, I mean, another example. This is what is a command line profiler. Okay, this is what you would see on the command line. But then there are the visual profilers as well. Okay, so for example, on the this is the visual profiler for band ratioing. So people from the geospatial domain, remote sensing domain, we most of the time to spectrally analyze the data, we do the band ratio, right? Certain bands, some kind of computation across the pixels located at the same position. Okay, so just look at this highlighted kernel. I mean, this one, the left side blue border one. So you would see the highlighted kernel in timeline. Okay, like it shows what time it is started, what time it ends, so how much time has been taken. So this is typically for this NDCI, that normalized differential cloud index, I think, or some oil spill index. So here it is calculating this band ratioing. Okay, hardly it takes 10.47 millisecond. Okay, you could see it here as well, that 10.47 milliseconds. Okay, and then So what kind of thread and grade configuration being used? So block size 32 by 32. So 32 by 32 threads. And then such how many blocks? 219 into 219. So this is how the arrangement is. Okay. So theoretical occupancy, it shows 100%. Okay. But it's just a theoretical occupancy. But here, if you will see the brown blocks, so each of the brown block are representing the transfer time. So the execution time for this entire process is quite very less, 10.47, but then for this data transfer, it is quite high. I mean, it's not been highlighted, but then looking at the size, the span of that particular block, we can imagine that how much of time is taken by each of these uh, image representing the spectral when captured with different spectra. Okay, so transfer 3 different images, and then you would see that these brown blocks for transfer time taken, and then this one for just execution. After that, we are just moving the results back, okay, to the device. That's how the visual profilers you can interpret. Okay, so basically, considering the different architectures, okay, and then HPC architecture and different kinds of operations we typically run on these remote sensing images, or for that matter, any of the images, like we typically perform the edge detection, segmentation, noise reduction, enhancements, or if you consider the convolution neural network, we perform the convolution operations. Then there are several morphological operations. What do? We just keep sliding the window, perform same operation across all the image, right? So that's, we just vary our sliding window across all the image. So all the morphological operations, convolution operations, proximity computation, histogram computation, band ratioing, explicitly applicable for the remote sensing images, then image transformation, horizontal, all those flips. This kind of thing can be done easily. Feature extraction. Okay, so all these are been done on the HPC platforms. So HPC platforms are quite good candidate to improve the speed up for such operations. And I would say, as compared to other, the GPU is the best candidate for this processing. Okay, so yeah, so I'll just discuss the case studies. Will present the work I have done earlier. I'll just try to finish it. I cover it briefly, but then I want to give that, this idea to you that how much of the communication cost, even if we use the HPC platform, for how much it matters. Okay, so this is about the oil spill detection, because the oil spill, it has, it's basically oil spill on the sea surface, which has adverse effect on the environment and economy, local industry, recreation activities, many different impacts are there. So it is essential to, and then whenever the oil spill happens, it takes many years to clean that oil, to make that region oil free. Okay, it takes several years. Okay, so Deepwater Horizon, which happened at Mexican Gulf of Mexico, I'm not sure whether it has been cleaned it or not. Still there are the this oil spill tracks. It's really very costly affair to clean it later. So better to detect at early stage, better to detect the spread. So that's why we had done this work, but then at early age to probably in near real time, so needs to be done, execution needs to be done faster. So applied the high performance computing technique, and then to evaluate, the different properties, say like the spectral properties, like the band ratio and the spatial properties of these images, we had selected different algorithms like the band ratio in case of the spectral properties, and for the considering the spatial properties, yeah, so Landsat 7 data been used here. So the connected components for spatial analysis, connected component identified, then for each of the component the morphological attribute profiles are been captured, and then for each of those connected component, what the attribute profiles captured are physical attributes and geometric attributes, broadly classifying. So geometric considering the elongation, solidity, slick complexity, orientation, and then physical attributes like gray mean and then standard deviation, and then there is a cascaded filtering, sorry, applied to it, and then all this processing entirely been done on the GPU and then MPI platform. So here, what I mean, because we all nowadays, even me, I mean, though I have the experience of GPU parallel computing in CUDA, which I have done during my PhD, but nowadays, whenever I analyze data, I never do any coding in C CUDA. I use PyTorch. Okay, I mean it's easy, so nothing wrong in using the platforms which saves your time. And yeah, I mean, a lot of, but then, of course, some of the things you must understand that what happens at the back end. For example, when I say that there is a pixel level parallelism, okay, so I had shown you earlier the timeline or the visual profiler for this NDCI, CPU NDCI, sorry, GPU NDCI, that function, if you're able to recollect here. Say this is the GPU NDCI. So it takes around 10.47 millisecond, okay, for band ratioing. So what happens in CPU that when we have to read any of the image, okay, so image is again a matrix, so we go cell wise, so row and column, okay, so we require two different for loops, each row and then each column for that row, so we require two for loops. So the complexity goes in terms of rows and columns. But on the GPU platform, what happens that each of the processor now holds the data element, say X, and that to be with the position, the location of that data element we calculate considering the block dimensions and the block index and then the thread index, because if you just, I mean, those are the details, like the thread get organized into block and block get organized into grid, so that way, so we can calculate the data position and directly we manipulate in parallel. So all the data elements get processed at one time because the processor already hold that data. Okay, so we have to just run the task just by checking on the boundary, like we are not trying to exceed the number of rows or in columns, and that's it. We doesn't require any for loop for that. Okay, so our complexity is something in terms of constant. Okay, there is no we can, I mean, there is the parallel computing complexity, I mean the the way we calculate on sequential, it comes in terms of rows and columns, number of rows into number of columns. So since there is no such for loop, it straightway reduces to a constant. Okay, so that's how what happens when you use GPU devices in your deep learning model. Okay, so yeah, so band ratioing is this execution is again showing the band ratioing. So here the blue line, it shows the execution time considering only CPU. Okay, and the red one is only GPU execution time considering only GPU execution time considering GPU, and the green one, okay, but then only the function execution time, and the green one is the function plus the data transfer. Okay, so function execution, whatever that NDCI calculation plus data transfer. Okay, so if we'll see, the communication time is 64 times more than the computation. Okay, the computation is just 0.01 for the image of size, say 18,432 by 18,432. That's how is the resolution of Landsat. Okay. So if we consider, if we do not consider the data transfer, then the GPU performs 412 times faster than the CPU. Okay, just imagine, if you don't consider the data transfer, GPU performs 412 times faster than CPU, but the moment we consider the data transfer cost, it hardly is 6 times faster than the CPU, but still it is efficient. Okay, it is still efficient because we have used the pinned memory. If you do not use the pinned memory, you would see this computation along with the data transfer would be more than or equivalent to whatever the GPU CPU has taken. Okay, so optimized data transfer matters a lot. Okay, so here there is one table. I'm just trying to uh, show you that how much of the time is been spent when you use unpinned memory and when you use the pinned memory. So, and again, as the memory size, as the image size increases, you get excellent performance on the pinned memory transfer. So 2400 by 2048 by 2048 pinned memory, if it takes 18.61 milliseconds, then unpinned memory takes 18.61, then pinned memory only takes 3.18 milliseconds. Okay, so see how much of a difference is there for the image of original size. If it takes 1000 milliseconds using unpinned memory, then it's just 247.44 milliseconds of pinned memory. Huge performance gain if you use the pinned memory. Okay, and so as I informed earlier, if you are using PyTorch, then please ensure that you are using this typical line while loading the data. In the data loader, always say pin underscore memory equal to true. It will do the same task for you. Okay, it will do the same task here what is been done. You will see the speed up, a good amount of speed up uh, over your data transfer. See, you don't understand that what is happening, but that's what is happens. Your data moves from your CPU. So basically, what is your host? Your CPU. Your data is on the CPU. Okay, GPU is different. GPU memory is different. Your data needs to move on the GPU. Understand this? So when it has to move on the GPU, obviously it should, if you provide some mechanism which would be faster, your overall performance will improve. So this is what is, yeah. So as I said, always there is not a single image we consider, right? There are temporal images, that the images captured at different timestamps. So for example, to detect the oil speed spray, you can say spread of the oil spill, the different images say captured at 1st May, then at 10th May, then at the 17th May, then at 26th May. So different images were captured. Again, the first image, if you'll see, okay, you would the images are with these strippings. Okay, so these strippings are just because there is a failure in the scan line corrector of this Landsat 7. So all the images you would see will be like this only. But then we know image processing, and then but then since it's a remote sensing images, the algorithms we need to use whatever they have mentioned for even this scan line correction. Okay, so after correcting that, so I'm just telling you the kind of pre-processing involved, but then same operation we do on this correction. So we have done that corrections as well on CUDA in parallel. So a lot of many pre-processing operations we know that. Yeah, here in the AI also, what do? We need to do some kind of brightness, sharpness, or rotation, flipping, right? So we do kind of augmentation. So while you do the augmentation, or I mean kind of transformation you apply on the data, there also you can use the GPUs. Okay, so yeah, that matters a lot. These are result. I am not no more interested in. I mean, since our focus is on this performance. So yeah, so of course the results are there to identify, to detect the oil spill from the sea surface. Okay, so these are the oil spill regions, you could say, after applying those cascaded filtering criteria. Then, yeah, this is something, the figure this typical diagram, it represents the because I'm trying to show something which everybody is familiar with. So morphological operations everybody is familiar with, right? The dilation or erosion operation. Okay, so here I'm purposely trying to share something which you are really very well aware of. Like in case of morphological operations, what do we do? Again, we slide the structuring element across all the pixels. Okay, so say 3 by 3 structuring element, then for that region 3 by 3 we find the mix or minimum value or maximum value, whatever our purpose. Then whatever the min max, we construct assign a new pixel to that particular location, right? And then we move to the next pixel, we slide our window to the next pixel, sorry. So and then so on, we just keep doing the same process again and again. But what happens when we do a parallel processing? Since we have our data is already been spread across multiple, so multiple processors already having their x1 y1 or x1 y plus 1 values. Okay, so all the allocations happens in parallel. Okay, then the computations like minimum maximum value computation, it also happens in parallel. And then the is for constructing the new image, whatever the pixel value is computed at each position, that is also been placed to that or stored to that particular pointer in parallel. Okay, so that's how there is no sequential approach. All the tasks been done in parallel, and that's why you get a good speed up. Okay, so morphological, again, if you, because C code, I'm trying to share it with respect to the C code, as everybody is familiar with this. And then I have also used the C CUDA. So yeah, so in this particular code snippet, here if you see that again, the image we scan through the number of rows and columns. Okay, and then structuring element we may uh, first scan vertically and then horizontally to improve on performance. But here, since this for structuring element we cannot avoid, okay, in CUDA also, because that is there. But then accessing nearby pixels is not that cost effective, because is cost effective because it has been stored in the shared memory, so faster. Okay, but then yeah, I mean, yeah, the complexity is in terms of the structuring element for the parallel computing, whereas on sequential computing it is the image size, that is the number of rows into number of columns, which you could see in the C code, but which is not there. So obviously it says that the execution time in the CUDA code is only depend on the structuring element and not on the image size. So it's independent of the image size. Okay, so computational complexity, rows, columns into structuring element, whereas for this it is only in terms of structuring element. On the GPU it is only in terms of structuring element. Okay, so here, yeah, this speed up, you would see for a single morphological operation, you will see the speed up over 220 times faster, okay, by varying the structuring element size. Okay, so maximum speed up observed is 220 times faster as compared to the CPU. Okay, just speed, I'll just try to, because yeah, so whatever we had seen, all these cases are of fine grained computation. The pixel level operations, the code snippet which I had shown, all are pixel level. So of fine-grained computation. Okay, fine-grained parallelism. Now comes the coarse-grained parallelism. Okay, which is based on the MPI high performance computing. MPI is basically the cluster. Okay, it's a cluster. So message passing interface. So so there is a concept of there is a root node and then there are multiple compute nodes. Okay, so and then each of the compute node has multiple cores. So what has been done, like the root process is there, like your root node, okay, master node, which if you remember the same thing, okay, I mean the same problem statement where we have extracted the connected components and extracted the features and all that. But then in what we have done in the MPI, just to, because I mean, as I said earlier, that we need to take care of the load balancing. So what we tried here doing, distributing the number of components equally across multiple core. So this is what is been the balance loading is been taken care. Okay, so root process, it is distributing the uniform number of components across multiple cores. Okay, so each core will get equal number of connected component. Again, as I said, that we cannot do the fine balancing. The reason is one of the component may be having say around 10,000 pixels, and then there is another component which may have say 30 million pixels or so on. Okay, we can't say. I mean, so we cannot do that level of fine balancing. But of course, I mean, at the component level, we try to give, say, if I have 100 components and 10 nodes, then each of the node will get 10 components that way. Okay, and then each core will extract the features like this: gray means, slick complexity, orientation, solidity, whatever. So each node will try to extract those details, the features, and then gathering all the features from this using the all reduce operation. So here all reduce and their broadcast all reduce, and then root process will collect the extracted features from multiple cores. Okay, so this is one, this is MPI based thing. But going ahead, we had also done the multi-level parallelism for the massive data set. Okay, so multi-level parallelism, what has been done? So there is a root process, okay, root node, which distribute the task across multiple cores. Okay, so we have seen that in the cluster there are multiple nodes. Some of the nodes may have GPUs mounted on that. Okay, so what has happened that we had say 100 components, connected components. Those connected components are divided across 3 different nodes. Okay, and then or 3 different core, just understand, I mean, but then each of the core or each of the CPU is further using its own GPU to calculate the feature for each of the component. Okay, so distributing components to the node. Okay, so this is something, the first layer. And then second layer are your MPI processing, and then third is your GPU core, where each of the core is giving task to the CPU, sorry, to the GPU mounted on the same node. Okay, so this is a multi-level parallelism. Okay, and then here is a result of the multi-level parallelism as well for so this is for extracting all the features. Okay, so a lot of sequential tasks were also I mean the part of this entire process. So overall the speed up, I mean considering everything, okay, data transfer, everything. So if 8 cores along with one K40, if it takes around 88.5 minutes to execute that, then for this many number of connected components, then for CPU, sorry, with because we were having 4 nodes with K40 GPUs, so with 64 cores in total, because each one is having 8 core, so total 64 cores, and this K40 GPUs it is almost 10.2, so almost 11 times faster than your sequential computation. Okay, not much speed up. The reason is a lot of sequential computations were there. So whenever you there are sequential computations involved, you would see the performance hampers or degrades because of this sequential task, because then we need to uh, either, I mean, it's very small, then again moving the data and then result to from CPU won't be sufficient, I mean won't be effective. Then probably you will do it on GPU, but then GPU is very bad in sequential computation. So yeah, I mean then you need to check that how much CPU takes the time for even moving the data, and then on GPU how much time. So you can look for that, I mean timing, and then can select where you want to perform the sequential operations. Okay, then there is a evaluation. So yeah, I won't focus much on this. Yeah, there's another case study on the earthquake data, again from the Haiti earthquake images of very high resolution quick bird. It is one image of around 29. It's just a single band because it's just a pan image, you can say. So one image of size 29,262 by 25,933. Again, you cannot process a single image. You will require multiple images to see the damages along with the time, maybe the before earthquake, after earthquake, and then yeah. So temporal data. So this is, we have followed the shift, the scale invariant feature transform methodology for that, where almost all these operations are been, what are the operations like Gaussian kernels. So applying, it's a convolution, basically all convolution computation, the GPU is the best candidate, right? But then whatever the other operations are also been executed on the GPU. Okay, so I'll just show you that GPU convolution and CPU, how much of speed up we have observed. Okay, so for 15,000 by 15,000 image size, the convolution kernel is around 57 times faster. DOG, the difference of Gaussian kernel. Okay, so difference, it's basically the difference between the two consecutive images whenever we formulate the octave for processing. So that's then extrema detection, the minimum and maximum value extraction, basically. So there also the GPU performs quite better. Yeah. So I mean, almost all the tasks, the GPU, the performance was even for the proximity matrix calculation, proximity calculation. This this plot represented as A is for the proximity calculation. Okay, and then the another one for minimum value extraction from that. Okay, but then yeah, of course, you can see that CPU takes around 525 seconds to do that, whereas GPU is just 0.90 seconds. Yeah, it's such a huge speed up, you will see. Okay, for proximity calculation, it's really 186 times. So you can even see that some of the a lot, if your data size changes. Okay, so this is the SIF feature, so 128 dimensions, feature dimensions, basically. So with this data size, the proximity, I mean, varying the data size, the proximity metric calculation, we see the improvements in the performance as well. The more speed up you get when you see, the more larger the data, more the speed up you will observe. But minimum value extraction, this is something, the task which is not purely purely parallel. So it's something which is not actually, rather I should correct myself, it is not actually depend on the input size. Okay, so everywhere you will see almost similar kind of speed performance. So it is, you will see the speed performance irrespective of the size of the data. So depending on nature of your computation, you will see the improvement in speed somewhere. The improvement would be there, but independent of the image size or data size. Yeah. Then again, similar work. So you use the convolution model, convolution neural network, and then yeah, this is result. But then more interest towards this with different high performance computing platforms like CPU, GPU, CPU plus TPU. Okay, and then distribution, the optimized distribution. Really, we get high performance as compared to other combinations like 16.81 minutes for seconds for processing that data for earthquake. Okay, so yeah, so here I would like to conclude and would like to share whatever being my findings, that yes, if you are using I want to use the high performance computing platform, for sure the GPU would be the best choice as compared to the MPI platform. Um, so because there are a lot of again communication cost is involved, we can optimize it, but then yeah, the architecture of GPU is very much complementary to the image processing task. So GPU is till now, I would say, the best candidate for processing the satellite images. Yeah, and then good amount of speed up we observe for different kinds of processing, like the typical operations we do, like convolution operations, morphological operation, proximity computation. So yeah, good performance improvement is observed. So yeah, that's what I would suggest you all um, working on this. Yeah, wherever possible to use a pinned memory. If there is a GPU, always use a pinned memory. So memory scaling is not possible with the help when you use the GPU, but then we can upload the data transfer, streaming can be done. Multiple GPU kernels can be written to move the data. Streaming can be done. Okay. So yeah, that's there. Okay. So yeah, that's it from my end. Thanks for listening me patiently. Now, yeah, if you have any question, please come up. I will try to answer.
Thank you, ma'am. There is a question from one of the participant. How does MPI improve the efficiency of large-scale geospatial simulations like hydrological or climate models?
It's there on the chat.
Yeah.
Okay, because the question.
Before
Okay,
2-3
so
minutes.
okay, so I'll just try to stop sharing. Okay. So MPI improves the efficiency. See, because here the message passing is something, as I said, that when you have the the whatever I just said if it's a different task of your um, climate model, I mean, whatever the different models you would say. So probably the different models would be running across, we just assume that multiple nodes, and then you are transmitting again, we can achieve the data level parallelism and task level parallelism over there. Okay, MPI is open for both data level parallelism and task level parallelism. Okay, so whenever we are, some of the things we must take care of is data transmission. So if you are sending the same data across multiple, then you should be using the broadcasting, and assume that if you are simulating, you may be trying in just like um, since I haven't worked exactly on the hydrologic or climate model, but then if you are doing some kind of parameter tuning uh, for this particular climate model, okay, or you may be trying on different methods, different analysis algorithms, then probably each node will run different algorithms, but on the same data. Okay, so basically every node will be having the same data, but it will run different algorithm on that data. So here you can achieve the parallelism. Okay, so that's how. And then efficiency always in terms of data transmission you can do, or you can formulate the large messages by merging multiple and then sending. That's how optimizing the data transfer. That's what I would say for this MPI platform.
Thank you, ma'am. We have one more participant raising hand here. Yes, ma'am, you can unmute and you can ask your question.
Ma'am, how do HPC system minimize data transfer overhead for fine-grained operations on GIS data?
Um,
Am I audible?
For yes, yes. So fine grained is we'll say for the GPU, right? So because there is how the GPU, because fine grained we cannot do it on the cluster MPI. So this is applicable only on the GPU, and GPU data transfer we can always optimize using the pinned memory. As I said that if you are using the PyTorch platform, then while data loading you can always say pinned memory equal to true. That's how we can optimize the data transfer. Yeah, I mean, is it what you are expecting? Please let me know if you have further questions to that.
Yes, thank you.
Is there any other questions, dear participants? You can unmute yourself and you can ask your question, or you can post it in the chat box as well. Yeah, there is a question from a participant, ma'am. In geospatial analytics, how do we decide the ideal grain size so that communication time does not exceed computation time?
Yes, so as I said, I mean the GPU, if you are using the GPU, there is a fine level, I mean fine grained computation we can do, because we don't have any other alternative. We have only the thread configurations available. So it is always a fine grained. But as I also shown you in the plots, even if the communication cost is high for the fine grain, still we get overall performance. I mean, in terms of overall performance, the GPU is faster as compared to CPU. Okay. So that's how I mean what I'm trying to tell here, that fine grained parallelism we do all on GPU, but when we do it, we may experience that we are paying more for communication. Okay, that means more communication cost is involved, but still the overall performance of execution, including the data transfer and the computation, we gain speed up over CPU. So don't much bother if you are getting overall computation gain on that, but you are using the fine grained distribution across the GPU, but you are running the sequential computation, then you have to be careful. So just and then I mean, for as long as you are using these packages like PyTorch, TensorFlow, you need not have to worry, because the system is, I mean, the packages are been designed in like the CUDA code behind that. You may not understand, but backend what it does, whenever the sequential task comes, straightway it sends it to CPU and execute it on CPU, and then the result is sent back to GPU for further processing. So as a API user, we doesn't actually realizes what goes in the backend, but that's what happens. So we need not have to really bother about this thing when we are working on this PyTorch or TensorFlow or any of the Python platform where we directly get the interface of this HPC. But this will come into picture whenever we have to write the parallel code ourselves, the way, because my contribution was there in writing or parallelizing the algorithm, right? So so I had to take care of that. But your objective is something different, like, I mean, it may be different, like no focus on the HPC, but yes, of course, you will be using HPC just as one of the enablers to perform it speedily.
Thank you, ma'am.
Yeah.
Yes, participants, any other questions?
Yeah, because I understand that the availability of this is quite, I mean, nowadays we use our laptops with the GPUs are there, but still, I mean, yeah, as the number of CUDA cores will improve, you will get benefit of that. So that is also one thing. And then the clusters, yeah, that's the availability of the cluster is also one of the concern, I would say, because yeah, I mean, not all the institute has that kind of setup. So that is also one. Yeah. So
I think there's no questions
no
further.
one can. Yeah. Okay. Fine.
Thank you so much, ma'am. On behalf of the APSIT and the organizing committee and all the participants, I extend our heartfelt gratitude to you, ma'am, for such an enriching session. Your expertise shed valuable light on how modern HPC system, the advanced AI models, and the programming language, the algorithm can work together to transfer the geospatial analytics. So we sincerely appreciate the time, effort, and knowledge you shared with us today. Thank you so much, ma'am.
Thank you. And thanks again to the organizers and the participants as well for listening me patiently. Thanks. Thanks a lot. Yeah.
Thank you, ma'am. Thank you so much.
Yeah. So, yeah. Uh, may I leave now? I mean, I can, right?
Yes, yes, ma'am.
Yes, ma'am.
Yeah, sure. Thank you. Thanks. Thanks.
Okay, dear participants, so now we are moving ahead for the online test and the feedback. Okay, so the link will be shared in the WhatsApp group, and as well as here in the chat you can see it. So we are requesting that everybody to give the test, and also you fill the feedback link whatever is given, because all these comes under the consideration of your certificate eligibility. So as it is displayed here, the test and feedback goes from 6:30 to 7:30 p.m. and 7:30 sharp we will be starting the validatory function session, like as we are ending, we are closing the FDP today. Okay, so even as we were engaging together and learning together, let us close it also celebrating together. So stay connected, and we all will meet back and again by 7:30 for the validatory. And till then, requesting you to complete your test as well as the feedback, whatever links has been, you can see the links is already put up on the chat box, and those who are in the WhatsApp, you can see the links are available. So please go ahead and complete it. Thank you so much.
We'll keep the meeting live. We'll be here in case if you have any difficulties, you can ask here.
Hmm.
Hello, Sarla ma'am, are you there?
Yes, ma'am.
Yes. So voice is audible?
Yeah, ma'am. Your voice is audible.
Okay. Your
Mine?
end also correct. Yes, correct, ma'am.
Okay.
Okay. Clear only, na?
Yeah, it's clear.
Okay. Thank you.
Ma'am, we'll start the session in next 2 to 3 minutes. Participants are still giving the online test.
Yeah, fine.
Okay.
Fine.
So we will. So we are back here for the valedictory program. So very good evening to everyone present here. A warm welcome to the valedictory session of our ATAL FDP. So learning may not end in sessions, but growth continues in spirit. Okay, so this is what the saying says. So over the past 6 days, we have been on a truly enriching journey exploring the latest advancement in geospatial technologies, geo AI, machine learning, and high performance computing. Our experts guided us through applications of SAR, geo AI for forest monitoring, and ML techniques in GIS, and explainable EO analytics, and deep learning based encryption. We also gained insights into regenerative agriculture and the role of HPC in large scale geospatial analytics. So today we gather not to mark the end, but to celebrate the learning, collaboration, and inspiration of this ATAL FTP that has brought to each one of us. So on behalf of AP Shah Institute of Technology, the organizing committee, the Department of CSE Data Science, I extend a warm welcome to our resource person, our esteemed speaker, HOD, the coordinator of the ATAL FTP, the co-coordinator, and all the faculty participant. And thank you all for your valuable contribution and active participation. With that, let us begin the valedictory ceremony of our ATAL FTP. So now I would like to invite the co-coordinator of this FDP, Dr. Veena Trivedi, to kindly present the outcomes achieved through this 6-day ATAL FTP.
A very good evening to all. Respected Dr. Ujjwala ma'am, Dr. Praveen sir, our head of the department, CSE Data Science, Professor Anga Iyer, the FDP co-coordinator, the coordinator, and my dear distinguished participants. As we gather here today at the conclusion of this faculty development program, it is a pleasure to acknowledge the significant milestones you have achieved. Over the past 6 days, you have strengthened your understanding of core geospatial concepts from coordinate systems to map projections, building a solid foundation for advanced spatial work. These fundamentals are the bedrock upon which all advanced geospatial analysis is built, and you now stand on that firm ground. You have also mastered the art of visualizing geospatial data to transform raw complex data sets into clear, insightful, and meaningful visual representations, visuals that can drive decisions and spark discussions. In addition, you have successfully learned to apply AI techniques, analyze complex spatial patterns, patterns that are often hidden within large and intricate geospatial data sets. By harnessing the power of machine learning and intelligent algorithms, you have opened new pathways for understanding the relationships, systems, and underlying dynamics that shape spatial phenomena. You have also gained the skill needed to build models capable of forecasting spatial trends, enabling you to anticipate future scenarios in areas ranging from environmental changes, urban development, public health, and infrastructure planning also. You have also acquired the ability to evaluate and implement real-time geospatial analytics, tools and methods that are increasingly vital in today's fast-moving research environment. And finally, you have achieved something even more profound, the readiness to initiate innovative research projects at the intersection of AI and geospatial data analytics. The ideas you have generated over this program, many of which are already taking shape, promise to contribute meaningfully to academic scholarships, community development, and technological advancement. Your commitment, curiosity, dedication have prepared you to shape the future of geospatial AI research and education. On the behalf of the organizing committee, I extend my heartfelt congratulations to each of you. May the knowledge you have gained continue to grow, the collaboration you have formed continue to flourish, and the innovations you pursue continue to inspire. Your dedication and engagement have made this program a success, and we look forward to the new directions your work will take from here. Once again, thank you all. So before handing over the control back to Salah ma'am, I just wanted to inform participants that your test marks and attendance will be updated on the portal in due course, and we will be informing the same information onto your WhatsApp group also. So kindly be a little patient, and once it is done, then you can give your feedback and you can generate your certificate. Thank you. Over to you, Salah ma'am.
Thank you so much, ma'am, for your encouraging words. So now, next I request our HOD, Department of CSE Data Science, Dr. Praveen sir, to share his remarks.
Okay, good evening, everyone. As we come to the conclusion of this 6-day AICTE ATAL FDP on geospatial data analytics, fusion of spatial science and AI. So I'm truly pleased to see how enriching and impactful this particular program has been for all of us. We know that over the past week, we have explored cutting edge technologies. We have seen number of concepts. We have seen certain practical applications. We have seen different emerging trends in spatial science and the artificial intelligence. Okay, the knowledge that shared by our experts, speakers, that has broadened our perspectives and given us new ideas to take back to the different research endeavors. Okay, so at this moment, I would like to take a few minutes to acknowledge the people basically who have made this particular FDP possible. So first, my heartfelt thanks to our management for continuously supporting us, continuously supporting our academic activities, initiatives that we are taking for the department, the encouragement that the management is providing us for the department to take such kind of programs, meaningful programs. So my sincere appreciation to our principal sir, okay, for his guidance, motivation, and the constant encouragement throughout the planning and the execution of this particular FDP. A special appreciation I want to give to the program team, we have Professor Anga Madam with us, okay, who is FDP coordinator. So Madam ensures that the smooth execution of our entire FDP with her excellent planning, coordination, and communication. Her dedication and timely management played a very key role for happening this particular FDP. Our co-coordinator, Dr. Veena Trivedi ma'am, she supported every phase of the FDP with a great efficiency and a commitment. Her proactive involvement and a constant follow-up basically help us to maintain the quality and the continuity throughout the all 6 days. And lastly, the Professor Sarla Miri ma'am for managing all the sessions, the communication and the logistic very smoothly at the back end. So your dedication, your timely coordination, your meticulous planning, and that basically ensures that every session run flawlessly. Okay, so I truly value the hard work of each and every my team members who put their efforts behind the scenes. Okay, so lastly, the to all the participants, that your enthusiasm, your punctuality, your presence, your active involvement into this 6 day FDP program, so that brought the energy to our FDP program. So it was wonderful to see such engagement from faculty members, from academicians who are participating to such kind of FDPs, and from different institutions. As the HOD of data science, I feel proud that our department could host such kind of FDP of this scale and relevance. So I hope that the insight gain here will definitely going to inspire further in learning, in research collaborations, and innovative teaching practices to the participants who have participated in this particular FDP. So I thank you once again to the everyone who contributed to the success of this particular FDP. Wishing you all the very best in your future professional journey. So have a wonderful evening. Thank you. Thank you, ma'am.
Thank you, sir, for your insightful and inspiring address. Thank you, sir. So now we are pleased to welcome Dr. Chaudhary ma'am, the eminent speaker, a leading researcher in high performance computing and data analytics. She's as a research fellow at London South Bank University. So ma'am, we are so glad and honored that you are in us. So I invite you to address the gathering, ma'am.
Thank you, Salla Madam. And it is my privilege today as we conclude this enriching faculty development program on geospatial analytics. So over the past days, you all must have explored a field that is rapidly reshaping the research in the area that specifically addresses the societal challenges where I mean, a lot of things like whether it's urban planning, environmental monitoring, disaster management, agriculture, or natural resource management. I mean, a lot of different domain, applications we could consider. So I hope this program has deepened your technical knowledge through the sessions on remote sensing or the GIS data analytics, spatial data modeling, then machine learning, AI, security of hyperspectral data, then relationship, maybe the ontological concept, then applying the, you can say, explainable AI, then of course the RS data security, then HPC for real-time analytical application. Yeah, so yeah, and many more. So I extend my heartfelt thanks to all the resource persons whose expertise and inspiring presentations brought new perspective to each of this session. Then also to the organizing committee, thank you for your meticulous planning, coordination, and technical support. As the head of the department has already mentioned, thank you for ensuring the smooth conduction of this FDP. It was really, I'm glad that it is really been planned and executed successfully. And finally, to all my fellow participants, Of course, your enthusiasm, then active engagement matters a lot. It's just one of the driving force for this program. So hope yeah, you'll carry forward the spirit of innovation we have cultivated here during this faculty development program. And so in closing, I hope that this FDP, faculty development program would be the beginning of new collaborations and ideas and new applications, as the head suggested, in the geospatial domain across multiple discipline. And I really appreciate that. I mean, this is something, the area which has a huge scope in India, where we have a lot of we are the agriculture country, we have the natural resources, and we need the environmental monitoring a lot. Yeah, so all those special domain, there is a huge opportunity to excel with in all technical aspect, considering the security, considering the real-time analysis, for generating the insights. Yeah. So thank you all once again for your dedicated participation, and I wish you success in your geospatial journey ahead. Thank you. Thanks a lot.
Thank you so much, ma'am, uh, for your enlightening words, and taking us to the journey of all the 6 days in a very short note. Thank you so much, ma'am, for this wonderful words. Okay, so now we are moving ahead. So there's a quote which says, "A program succeeds not only because it is organized, but because participants bring it to life." The participants are the real heartbeat of a successful program. So participants are not just attendees, they are co-creators of the success. So now we are going to go forward and listen to some feedback from our participants who had been in this journey of the 6 days ATAL FTP. So I humbly request Tayeb Ali sir from Don Bosco Institute of Technology to share your valuable feedback, sir.
Uh, Hello, good evening. Am I audible?
Yes, sir, you're audible, sir.
Yeah. So the FDP on geospatial and AI was very insightful for me, and yes, it was very well structured. The speakers were excellent, with a deep knowledge of spatial as well as AI domain, and I would say they explained from beginning to the complex topics very well with very great clarity. As a beginner who is just starting my research journey, I found this FDP very useful because I had to understand overall landscape, where to focus and where to work. So once again, sessions were very thoughtfully designed, from like basics to advanced topics. So every expert speaker started from the basic fundamentals and went till the higher. So there was something for the beginners as well as for the advanced learners. There are a lot of doctors who are as a participants attending this FDP. So I particularly appreciate a lot of discussions which happened on Q&A, explainable AI, and specifically lots of real world examples were given, which are practical and which are relatable. Finally, I would like to thank first AICTE, then APSIT, and then organizers of the department, CS AI department, specifically Professor Anagha ma'am, Dr. Veena Sarla ma'am, Head of Department, Dr. Praveen sir, for organizing such a great, excellent FTP. And yeah, overall, it was a very highly valuable learning experience. Thank you so much. Thank you.
Thank you so much, sir, for your valuable feedback. So now I request Ranjita Asti ma'am from Taku College of Engineering to share your experience in the 6 days journey, ma'am. Ma'am, you're there?
Ranjita ma'am, you're on mute.
Am I audible, ma'am?
Yeah, yes.
Good evening, everyone. It's a great pleasure to share my feedback here, actually. This FDP has been an excellent platform to understand how spatial science, remote sensing, and AI come together actually to solve the real world problems. The sessions collectively actually that depend or broaden our understanding of modern geospatial AI. Many sessions actually, all the sessions highlighted the importance of explainable and interpretable models in Earth observation. Also, we learned about the innovative approaches such as hyperchaotic encryption for hyperspectral images and scalable deep learning architectures for real-time geospatial processing. Also, the sessions connected this geospatial analytics with practical applications in sustainable agriculture and emphasize the growing role of high performance computing, which we have just in today's session we come to know about this HPC. Then this FDP has been an extremely enriching, I can say that, insightful and impactful. Through this FDP we gained valuable insights into cutting edge tools, algorithms, applications and research trends that will greatly benefit us to work in geoinformatics and AI. So the expertise of these distinguished speakers, we can say, that broadened our understanding of both theoretical concepts as well as practical significance. So I sincerely thank all the experts for sharing their knowledge, and I appreciate AP Shah Institute of Technology and the wonderful committee, actually all the team members, Dr. Meena ma'am, Anagha ma'am, Sarla ma'am, for their wonderful, very well organized session, FDP, and also AICTE ATAL for organizing such a high quality and meaningful program. Thank you so much. Thank you so much, everyone.
Thank you so much, ma'am, for sharing your experience with us. And we are glad to hear that you have a very good experience for the last 6 days. Thank you, ma'am.
Yes, ma'am. Thank you so much.
So now we have Sonali Patil, ma'am, from PCCOE Pune. So I request you, ma'am, to come up with to share your feedback here with us.
I hope I am audible.
Yes, ma'am, you are.
Yeah, I'm Sonali Lunawat and I'm from PCCOER. And I just want to start with a very good evening to everyone. I would like to express my sincere appreciation for the AICTE ATAL online FDP on geospatial data analytics, a fusion of spatial science and AI. Over the past 6 days, the FDP was been extremely enriching and thoughtfully designed, combining both the foundational concept and advanced applications. Each sessions offered a unique perspective. The inaugural talk and the introduction to machine learning application in GIS gave a strong conceptual base for me. Sessions on disaster management using GIS, explainable AI models, SAR data interpretation, and geospatial feature extractions were particularly insightful and showed how AI can significantly enhance in geospatial. I especially appreciate the real world demonstrations as well. The experts from NASA, IITs, and German Aerospace Center were highly knowledgeable and they have presented even complex concepts in a very simple way. The inclusion of the case studies, practical applications, and interactive discussions helped me to bridge the gap between the theory and the real world implementations. Overall, this FDP has broadened my understanding, and I am now keen to work in this domain. And it has inspired me to explore more deeply. I am very much thankful to the organizers, the coordinators, and all the resource persons for putting together such a comprehensive and well coordinated program. Thank you once again for this wonderful learning opportunity. Congratulations, team, and especially thanking Anaga ma'am, Veena ma'am, and Sarla ma'am. Thank you so much for providing such a nice and wonderful FDP. Thank you so much.
Thank you so much, ma'am, for your wonderful feedback, and we are so happy to hear that the ATAL FTP has impacted you with so much of knowledge and so much of impartation, which has encouraged you to go ahead. Thank you so much, ma'am.
Thank
And
you, ma'am.
yeah, and the platform is open for any participants. Okay, so anybody willing here, you can unmute yourself and you can share your experience so that we may also know, like, what has been impacted the 6 days journey to you all. So if anybody here, the
Good
floor is
evening,
open.
ma'am.
Yeah, yes,
Am I
yes.
audible, ma'am?
Yeah, you are, sir. You can.
Ma'am, this is Dr. Namdev Vade from Thakur College of Engineering Technology. So in the last year, I've done the PhD in the same domain. But in spite of that, whatever the knowledge I have gained in my that during that PhD period, but I don't think that whatever the sessions and the experts have explained very nicely. So I'm very what we can say, very much impressed whatever the topics and the session all the experts they have shared, because everyone they have talked about that respective factor expert and the sessions. So the most important thing I like in the all the sessions that your question and answer sessions, because normally I daily ask some questions to the experts, and I know the time is that, but your experts and the speakers are very humble, and they are never like that. They don't want. They are not giving the answer like that. They always explain each and every point which of the question I've raised very nicely and neatly. So congratulations all of you, your Anaga ma'am, and especially our AP Shah College Institute of Technology, and a special thank to our college also and management also, that they support us to have attend this kind of the sessions. Thank you very much. And in the future also, if there is such sessions are there, we will definitely that attend your sessions. Thank you very much, ma'am.
Thank you so much, sir, for this, for the valuable feedbacks and sharing your experience with all of us. Is there any other participants who wanted to share your experience? Okay. Anybody in the chat? Okay, fine. So thank you so much. Okay, so now moving ahead, so we are coming to the conclusion of the ceremony. So before that, uh, I request everybody to just, we want to have a photograph session with you all. So requesting all to just keep your video on for a few seconds. So, and have a beautiful smile in your face. Let us say a cheers and we have a photograph, because it's a 6 days journey. It might create a memory as well. Yeah. So thank you so much for your cooperation. So requesting everyone to please keep your photos on. And I hope the photograph team is taking it. Yes. Yes, thank you.
Deepali ma'am, please confirm once you are done with the
Yes,
screenshots.
yes.
Yes, ma'am.
Yeah. Deepali ma'am, is it done?
Ma'am, just for 1 minute.
Okay. Deepali ma'am, you're there?
Yes, ma'am, done.
Okay, okay.
Thank you.
Thank you so much. Thank you so much, dear participants, for your cooperation. Yeah, yes. So we are coming to the last, the conclusion. Yeah, just a minute. Yes. So finally, to conclude the ceremony, I request our coordinator for this ATAL FDP, Professor Anaher, who is the pillar for this entire FDP, to be, for all the 6 days what we were experiencing. So I welcome you, ma'am, to deliver the vote of thanks.
Thank you, Sarla ma'am. Very good evening to everyone. On behalf of AP Shah Institute of Technology, I, Anaga Aher, coordinator of this FDP, would extend my heartfelt gratitude to all our distinguished experts, our participants, supporting faculty members for making this ATAL FDP a grand success. I would also like to mention that for this FDP, we have recorded an excellent response of 199 participants across the India. We are truly grateful to our speakers who have shared their time, their expertise, who have guided us, whether it is 9, 9:30, 9:45, they patiently answered all the queries which we had during these discussion sessions, I'll say. We have expertise from NASA Impact. We have our guest speakers from German Aerospace Center, IITs, London South Bank University, many international universities, as well as we had many industry experts who guided us throughout this journey. Sincere thanks to our keynote speaker for today, Dr. Ujwala Chaudhary ma'am, for joining us. Also, I would like to thank Dr. Sangeeta Chaudhary ma'am, Dr. Ujwala Bharambe ma'am, Dr. Surya Durba sir, and all our distinguished experts. I would extend our thanks to Principal sir, management of AP Shah Institute of Technology for their continuous encouragement. And I would like to thank all our participants for their enthusiasm, the engagement, the time which you have put for making all these 13 sessions a wonderful journey of learning. Along with this, I would like to thank our organizing committee, Dr. Veena, Professor Sarla, as well as our HOD, Dr. Praveen sir. So thank you once again for your time, your support, and active participation for these 6 days. Wishing you all very best in your academic and research journey. Thank you. Thank you so much.
Thank you so much, ma'am, for your kind words and making everything possible for us and helping us for this 6 days, gaining new insights and new things which we have experienced and we are learning into a different domain. Thank you so much, ma'am. Thank you. So yeah, so FDPs may conclude, but the inspiration, the spark continues to lead us forward. So as we conclude this ATAL FDP, let us carry forward the knowledge, the connections, and the inspirations we have gained through this entire 6 days. So thank you for your wholehearted participations. So wishing you all the best and a very goodbye, and may you continue to learn, grow, and excel. Thank you so much. So with this, we are concluding our entire FDP. Thank you.
Thank you, Ujwala ma'am.